Hi guys, what's up? What's up? What's up? Are you all able to see me and hear me? Am I audible? Hello, people. Can you guys see me? I am still not live. Uh, oh, I am live. I am live. I kept thinking that I'm not live. Hi guys, are you all able to see me and hear me? You should have said yes. If you guys would have said yes, I would have understood. But anyway, no worries. Just a second. Yes. Hello, 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 everybody. Like I always say, Andiriki Namaskaram, Ellargu Swagatam, and a very warm Vanakkam to Vedantu JEE English channel. This is me, your master teacher, Nabamita Bhattacharji, and today we are here to cover this high weighted chapter that is entitled as Thermodynamics. So, how are you all? And I hope that you all are absolutely excited because we have seen a lot of questions from this chapter, and we are going to complete this chapter A to Z. Everything that you have thought about this chapter, we are going to cover it today. So, hello everybody, hello everybody. I can see, yes, I will be doing P block and periodic properties in the next session. That is in this coming Monday. Coming Monday, I will be doing P block and periodic properties. After that, I will be doing mole concept and solutions. And with that, we will be covering all of your high weighted chapters. So, I believe that if you stick to this channel, you will be getting a lot of benefit. Yes, so quickly go and call up your friends, people, because we are going to do a flash series and I will be covering end to end every single thing. Yes, so I can see a lot of student, Anugna, Alia, only spectrum, Trishya. Hello people, very good evening. Yes, so do we have a pen and paper, people? Do we have a pen and paper with you all? Because we will need a pen and paper. Yeah, we need to make some notes. If you have already made the notes, then highlight the notes when I tell you that this is important. So yeah, okay. Shall we then? Shall we? But quickly go and call up your friends. But before I start with the session, let me also tell you that this is the schedule of 1st January to 6th of January. And today we have reached 4th of January already, which is why at 6 o'clock, no, at 6:05 I started with thermodynamics, and I believe that I'll be able to cover it by 8:30. All right, and then tomorrow you have alcohol, phenols and ethers by Pahul sir. Then you have vector and 3D geometry by Namrata ma'am, and tonight at 9 o'clock you have ray optics, for which you have been dancing on Shreyas sir's head for a very long time, isn't it? And Saturday, as usual, you are going to have a marathon session. All right, everybody. Yes, the chalo, shall we begin, everyone? Shall we begin, guys? Are you all with me? By the way, why do I see that there are very less students? Why are there less students? You guys are not interested in thermodynamics? What is it? What is it? Will this session be? Yes, absolutely. It will be useful for 2025 students as well. But what happened? Why do I see less number of students? Guys, quickly go and call up your friends not liking this. Not liking this. Yes. Quickly go. I am good, Akshay. I am good. Much better right now. Yes. Hi, Arvind. Hello, Bacha Party. Chalo, let us start with the session. Yes, I'm not going to spend a lot of time here. Okay. So first of all, the question is that why are we studying thermodynamics? Yes, because this is one of the high weighted chapter and it is coming in JEE. Is that all it is? No, no, bacha. No, we are not studying thermodynamics just because it is coming in JEE and just because it's a high weighted chapter. You have to understand that thermo means heat and dynamics means changes, right? Now, when we study chemistry, we understand that there is a formation of bond, there is dissociation of bond, and you understand that when there is formation of bond or there is dissociation of bond, there is heat energy somewhere in the picture, isn't it? There is heat energy that is consumed when you want to break a bond, and there is heat energy that is released when you when you form a bond. Do you remember that that diagram we have studied during chemical bonding? Do you remember that? Yes, like there are two atoms. These two atoms are at a higher energy, and when they form bond, it comes at the bottom. Do you remember? Yes. Do you remember, everybody, that there was a curve? There was a curve when they formed a molecule. There was formation of bond, and at that point of time they were stable, so the energy came down. Exactly my point. So when they form energy, they are more when they form a bond, they are more stable. Lesser is the energy, and we all know that when energy is less, that means that the system is stable. Now, I have just told you about one basic definition of, I have just used one basic term of thermodynamics, right? So in thermodynamics, you come across certain definitions such as what is a system, what is a surrounding, what is universe, what is entropy, what is enthalpy, all of these, yes. And that is why we are going to study them one by one. Now, right here, today I am not going to write down everything. Why? Because it consumes a lot of time when I'm writing down everything. I will definitely write down what do you call it? The derivations and everything. Don't worry about it. But the definition, I'm not going to write it. It's basically just English, and no one is going to ask you definitions in your JEE exam, right? So first things first, everybody, in thermodynamics, it is the study of heat, thermo, and work, that is dynamics, right? I have just told you this. I've just explained. Now, what does it do? It deals with energy transfer during a chemical and physical change, and how we can predict whether the given change will occur or it will not occur. Now, thermodynamics, although the chapter is important, we also have to understand that it does not come without some disadvantages. Yes. What are you guys saying? Video is not see. What are you guys saying? No, everything is clear. I have also logged in as a student, and I can see that I'm absolutely clear, guys. What are you saying? Look at this. I'm absolutely fine. What are you saying that it's not clear and all? It is absolutely clear. Yes. So what thermodynamics cannot do is that it cannot tell you the speed of the reaction, which is why we study another chapter that is called as chemical kinetics, right? It cannot tell you the path of the reaction. What path has the reaction taken? It cannot tell you. It is not applicable for microscopic environment at all, and you have to understand that all the laws that we study in thermodynamics chapter are related to macroscopic. Do you understand what's the difference between macroscopic and microscopic? For example, today or tomorrow, if I had, like, I recently had fever, right? Nobody cared. No, none of you would care if I have fever, if I am not well or anything like that. But when the whole world went through pandemic, when the whole world had a fever, when the whole world was suffering from cold, that time we did care, right? Yes, that time we did care. Why so? Because at that point of time we were talking about something that is on a macroscopic level. What is macroscopic? You understand, we were talking about the whole world. But microscopic level, just my fever, my cold, nobody cares. Who cares, right? It's all about you take classes, you are fine. You don't take classes, okay, all right, you are probably not fine. So do you understand? This is the difference between microscopic and macroscopic. So when we talk about thermodynamics, the laws are applicable for macroscopic systems. Yes, but it is not for microscopic level. Yes, all right, everybody. Do you guys understand this? Do you guys understand this? Great. So this is all about thermodynamics, right? So overall, once again, reiterating the fact, everybody, that thermodynamics is the study of heat and change in the work done, or bond breaking, bond breaking, bond forming. There are changes which are related to heat, which is why we have to study thermodynamics in chemistry and not just in physics. All right, yes, everybody. Okay, so now here comes some definition that we have to understand. First of all, what is a system? First of all, we have to understand that what is a system. A system in thermodynamics, everybody, a system in thermodynamic means a part of universe. Universe, you understand? Universe, you all know, right? What is this? All of your planets, your galaxies and everything, right, together, it's all universe, isn't it? Andromeda galaxy, blah blah galaxy, this galaxy, that galaxy. Together, everything comes as a universe. So in thermodynamics, we're not talking about the whole universe. In thermodynamics, basically, what you have to understand is, let's say that this is a glass. Let's say that this is a glass, right? So this glass, whatever happens in this glass, this becomes my system. But this glass is present in my hand, this glass is present in this room, this glass is present in front of the camera. Everything together becomes your universe. Just this glass is your system. Apart from this, everything else that is around it, that becomes your surrounding. So surrounding plus system becomes your universe. Do we understand this, guys? Do we understand this, everybody? Yes? What did I say? A system in thermodynamics means the part of the universe which is under observation. What are we looking at? We're looking at the glass. So this glass is our system. What is it that you are not looking at? You are not able to look at the green screen. You are not able to look at the light. You are not able to look at the camera. You are not able to look at my laptop, my table. Are you able to look at it? No, but the glass is present. The glass is present, right? This glass is present in front of you. I am present in front of you, but you do not look at anything else because those are surrounding. And surrounding plus the system together becomes your universe. Do we understand this, everybody? Can I have some hashtag EPBT in the chat box if you have understood, everybody? Yes? Can I get some hashtag EPBT in the chat box if you all have understood this, everyone? Yes or no? Yes, all right, yeah. Now, the system can be of two kinds. One is your open system, one is your closed system. So, guys, let's understand this, okay? What is open system? What is open system? Let's say that your mom is, your mom or your dad, yeah? Let's say that in your house, your mom or your dad, they cook. And today they were not able to cook for some odd reason. They were not able to cook, right? Okay. So, you were asked that, bacha, go and cook something. Now, either you can take a pan in which you can put some salt like this, you can put some turmeric like this, you can put some oil like this, you can fry it like this, blah, 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 right? But you can also take a pressure cooker. And in the pressure cooker, everybody, you tell me, once you close the lid, can you put some salt? No. Can you put some water? No. Can you put anything else? If it is burnt, it is burnt. You have closed it. You have closed it. But in an open system where you had the pan, you could do a lot of things with it, isn't it? Yes, yes, yes. Right, guys? Right? Right, everybody, are you guys understanding? So what is it? What is an open system? In an open system, there can be an exchange of matter. See, I just told you, matter. What are you adding? Salt. What are you adding? Water. What are you adding? Oil. What are you adding? Some onion, some garlic, some ginger you are adding. You also want to add a little bit of soya sauce, let's say. But you get the point. So in an open system, there is exchange of matter, and sometimes, let's just say that the oil was too hot and you just chapak, you put it, what happened? The oil escaped out of the pan and it hit you somewhere. And maybe there is a blister, some sort of blister. So what happened? There was exchange of matter, and also when you stand in front of the pan, you can feel that it is hot. You can feel that it is hot. So there is exchange of energy as well. Do we understand this? Yes. So there is exchange of matter as well as energy with the surrounding everybody. But in a closed system, everyone, when we are talking about a pressure cooker, the pressure cooker, if you are near it also, it whistles. It does whistle. Yeah, I know, it whistles. But when it is not whistling, can you even understand if it is hot enough? Is it hot enough? Why is it not whistling? Sometimes you cannot understand all of these things, can you? So you have to understand that in a closed system, there is exchange of energy but not matter. How? If you just try and touch, don't try it, please. Later on you will blame me, so don't try it. If you just try and touch the pressure cooker, you will understand that it is hot, isn't it? It will be hot. Yes, my dear students. So what can we say? I'm just telling you the same similar thing. I am telling you that there is exchange of energy, but there is no exchange of matter, because now you're not able to eat. Now you're not able to add salt or water, or you cannot be that salt bay and with all that style and all. Can you put? No. You cannot put anything. Is this clear, everybody? Do we understand what is the system? Great. So I just told you that system can be open system, closed system. Oh, acha, there is another system which is called as isolated system. Now, what is this isolated system? Isolated system, everybody, have you seen a thermos flask? You must have seen a thermos flask, right? So in a thermos flask, what happens? In a thermos flask, you can keep hot water in it for one whole day, but there is no exchange of energy or matter. You are not adding water, you are not taking away water from there. You are not understanding thermos flask from the outside, it is actually not very hot, right? So you must have added something hot, but when you're touching it, you're not understanding if it is hot or it is cold. You cannot, right? So that means that there is no exchange of heat, there is no exchange of energy, there is no exchange of matter. Now you have to understand one thing. Let us say that, everybody, let us just say that, okay, everyone, please try and understand this. Yeah, let us say that I am drawing here a container. Okay, I'm drawing here a container. Now, for the open and closed system, everybody, this particular wall, it is called as a dithermal wall. Okay, this is called as a dithermal wall, and this permits exchange of energy and matter. But when we say that we have, everybody, an isolated system, right? In an isolated system, do you know what wall do you have, everybody? Yes, do you know what is the wall that you have? In this case, you, my dear students, have an adiabatic wall. What do you have? You have an adiabatic wall, which does not allow exchange of mass, matter, or energy. Dithermal wall can do so. So dithermal wall is present in the open and closed system. Adiabatic wall is present in your isolated system. Am I clear, everybody? This is clear. Great. Okay. Now what happens before we understand intensive properties and extensive properties? Now we have to understand that there are different types of thermodynamic process. What do you have? You have different types of thermodynamic process. Okay, what are this thermodynamic process? You have isothermal process, you have isobaric process, you have isochoric process, you have adiabatic process, and you have cyclic process. What is isothermal process? From the name itself, we can understand that iso means same, thermal means temperature. That means the processes that are carried out at constant temperature is called as isothermal process. So that means that dt is equal to 0 here, everyone. Can you see? Can you see temperature remains constant throughout the process? That is why I said that it is carried out at constant temperature. Great. Now when we say barik, the moment we hear bar, we understand that bar is a pressure unit, isn't it? Bar is a one unit of pressure. So we see that here pressure will remain constant. That means any process that is carried out at constant pressure will be called as isobaric, and here dP is equal to 0. Great. Moving on, what do you have? Moving on, you have isochoric process, everybody. And isochoric is related to volume. So when you carry out processes for which your volume has to be constant, you call that to be as isochoric process. And right here, dV will remain as equal to 0. Then we come to adiabatic. What is adiabatic? I've just told you. What is it? Adiabatic, where there is an adiabatic wall, where there is no matter or energy exchange happening. That means that in adiabatic process there is no heat transfer between system and surrounding. The system cannot exchange heat with the surrounding, and here dq is equal to 0, everybody. Yes, what will you have? It will dq is equal to 0. And finally, we come across another process that is called a cyclic process, where the initial and the final states are same, and it also forms a loop, by the way. It also forms a loop. That is when you have a cyclic process. Somebody is asking me, ma'am, is dithermal the one in which allows change of temperature? But a dithermal wall, as I have just told you, that dithermal wall can exchange energy. Okay, it can exchange energy. And yes, when we say energy, what do we mean? Heat is a form of energy. So yes, dithermal walls can allow the transfer of energy. You are right, Samanyu. Okay, you are right. So are we clear with all of these things? Great, we are, right? Now we come across something called as state function and path function. Now you know what happens. Okay, let's say that State function and path function. Okay, we try to understand this, everybody. So you all know that for your JEE exam, right? For your JEE exam, what do you have? You have a 75% criteria in a board exam, right? But does anybody, after you are done with your board exam, does anybody come and tell you that, oh, how did you study for boards? Yeah. How much time did you give for boards? Yeah. Nobody does that, isn't it? But for your JEE exam, once you get a good ranking, everybody, all the news channel, everyone will be behind you and they will keep asking you, please share your secret success story, no? Please tell us, how did you get this success? Please tell us how did you get to, how did you get so much marks? Everybody will ask you this, isn't it? So do you understand now that your board exam is based on state? It's a state function. Why is it a state function, bachos? Why am I saying that it's a state function? Because nobody cares about how did you get that 75% criteria. Everyone is just asking you one question: did you get 75%? If you did, you get an admission in your JEE, right? But once you get a good ranking in JEE, all your coaching institutes will also come and ask you, please tell us, no, how did we help you? How our mock test help you? How our test series help you? Everybody will do that. Right? So do you understand what is a state function and a path function? The state function does not care about what path you have taken, what journey you have followed. Nobody cares about that. But your path function does care about it. That acha. Oh ho 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 ho. So you are saying that you have done work. What work? What kind of work? Why did you do the work? So all of those things, it's a path function. Yes, your work, heat transfer, that's a path function. What is a state function? Delta U, that is internal energy. Delta H, yes. Delta G, in delta S, or pressure, volume, temperature. Nobody cares. How did you increase the pressure? Why do I care about it? All I care about is pressure at initially it was 10 atmospheric pressure. And finally, it was 5 atmospheric pressure. I only care about that much. That's it. So that is why that's my state function. Do we understand? Now, state function is a property of system that depends on the state of the system, right? Yes, like enthalpy, entropy, internal energy, free energy, all of that is your state function. What is a path function? The property of the system that depends only on the path by which the process is done. For example, work and heat. You know what? Let me give you a physics example. I think physics example you will understand better. So you have distance and displacement, isn't it? Distance is a scalar quantity, displacement is a vector quantity. Am I right? Now in displacement, do you care? Do you care? Displacement, what happens? Displacement is the shortest distance and it can be zero. Nobody cares. In displacement, do I care about what path you have taken? No, but if you take a certain path, your distance can increase. So your distance is a path function, displacement is a state function. Do you get it, everybody? Am I making myself clear, everyone? Do we understand, guys? Do we understand, everybody? No? Yes? Can I get some EPBT? Hashtag EPBT, everybody. Hashtag EPBT. If you have understood all of these, please quickly go ahead and let me know that you have understood this. All right. Now we understand something that is called as extensive and intensive properties. What is this? So what happens is you have to understand that an intensive property, it does not depend on the amount of matter present in the system. For example, everyone, on earth, what is the population? Who cares? The pressure is still going to be the same, right? The pressure on my head, the pressure on Raghav's head, the pressure on Trisha's head, the pressure on Amit's head, everybody has the same pressure that the air molecules are exerting. Does it care? Does it care? Does the air molecules, do they care that, oh, from today, there is 10 billion extra people on earth, so I think we should change the pressure? No, it doesn't. It doesn't. Hence, do you understand that properties that do not depend upon the amount of matter that is present in the system, that's called as an intensive property. So what are your intensive property? Your intensive properties are temperature, your intensive properties are pressure, your intensive properties viscosity, surface tension, vapor pressure, melting point, boiling point. These are all your intensive property. Now we come across something that is called as extensive property. Your extensive property, they care. They care. What do? They depend on the amount of matter that is present in the system. For example, okay, what is my weight? Tomorrow my weight can change, right? My weight can change, isn't it? Now you go to the moon, your weight will change. You go to the lift, your weight will change. You go to what? You go to Northern Ireland, your weight will change. Because what will I do? If I go to Italy or France, I will eat a lot of maida, isn't it? I will eat a lot of croissant and I will eat a lot of cake and pastries and everything. My weight will increase. My weight will increase. So you understand that weight is actually an extensive property because it does depend on how much matter do you have. Yep. Is this clear, everybody? So now do you understand? So pressure, mass, volume, heat capacity. Yes, heat capacity, internal energy, gives free energy, enthalpy. These are all your extensive properties. Yes, everybody? These are all your extensive property. Yes, thank you so much, Anugna. Anugna is saying that easy peasy biryani tasty. That is what EPBT means. So I hope that till here, intensive property, extensive property, are we done with all of these, everybody? Do we understand this, guys? Do we understand this? Yes, we do. Yes, we do. Now, you know what, Bachus? Now we have to come across something that I haven't been, that I was telling you. Now we will come across something. I kept saying internal energy all this time, right? Isn't it? I kept saying internal energy, internal energy. So everybody, now we are going to understand this internal energy. Okay, let us try to understand this here. But just a second, I need a little bit of pages. Okay, all right. Now, before we start your first law of thermodynamics, now we are going to understand what is internal energy. The internal energy, everybody, what do you understand by the term internal energy? By the term internal energy, do you understand that energy inside, right? Energy inside. So that means that, remember I was telling you that this glass is your system. So basically when we say internal energy, now in this glass, just imagine that there is some amount of water, there is some amount of gases. The gases will be randomly moving, that means there is some kinetic energy. The water molecule is here. So let's say that because the water molecule is not moving, the water molecules are not moving, let's say that they have potential energy. The moment they evaporate, they will also have kinetic energy. Apart from that, let's say that there are some bonds that are breaking because of that evaporation or condensation, whatever is happening. So let's say that there is bond energy also. So now do you understand that in this system, right in this glass, my God, there are so many energy. There is kinetic energy, potential energy, bond energy, blah, blah, blah energy. So when I say internal energy, I mean the energy, the total energy that is present in the thermodynamic system, and it is the sum of all the energies, the kinetic, the potential, the bond energy, everything. The sum of all the energies together becomes your internal energy. Okay, all right. And it depends on the quantity of substance, because we just said that it is an extensive property. So now you understand, what if there is more amount of gas, what if there is more amount of water vapor, less amount of water, that means your kinetic energy is slightly more now and potential energy is maybe a little less. So do you understand how it is depending on it is depending on the amount of substance that you have, right? Now, so everybody, we also said, I also told you that this is a system. Your system can be open, your system can be closed. You cannot measure, you cannot calculate the absolute value of internal energy, because let's just say that I went to measure it, but while I was measuring it, some more water molecules became water vapor. How will I do that? I will not be able to calculate. You can only change, you can only calculate the change in the internal energy, but you cannot calculate the absolute value of the internal energy. So I think, my dear students, let's first write all this down, because otherwise everything will be like poof, gone away from our mind, isn't it? So let us write that down. Yes, we are talking about internal energy. Yes. And this internal energy, my dear students, it will be denoted in your book. Sometimes it will be denoted as U, or sometimes it will be denoted as E. It can be anything. But understand that even if in your exam you get U or E, you have to understand that we are talking about internal energy. All right, everybody. So let us write that down. What did I say is internal energy? Internal energy is the total energy. Yes. Internal energy internal energy is the total energy contained, yes, contained by a thermodynamic system. Yes, by a thermodynamic system, right? Yes, then what did I tell you? I told you that it is the sum of all energies. It is the sum of all energies. And when we say sum of all energies, bole to it is kinetic energy plus potential energy and dot 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 many other energies, whatever that is. Okay. All right. Yes, it is an extensive property. It is an extensive property and depends on amount of or quantity of substance. Okay, depends on quantity of substance. All right, and finally, what did I say? You cannot calculate absolute you cannot calculate absolute value of internal energy. You can calculate what can you calculate? You can calculate the change in internal energy. All right, you can calculate the change in internal energy. All right, guys. Yes, now don't worry, I will be sending you the notes. So even if you are not writing, I think it's absolutely fine. All right, I think it's absolutely fine. So don't worry about it. Sure. Now moving on, you have to understand that the delta U of the system, the internal energy, right? Not delta U, sorry. Internal energy of the system. When can it change? When will you be able to change the internal energy? I believe that the internal energy will change when heat passes into the system or it escapes out of the system, right? I believe that the internal energy will change when, let's say that I have done some work on the system. For example, what if there is let's say there is, let's say, some amount of chemicals, and what I did was I took a spoon and I stirred it. If I stir it, then what happens? What happens? I have just done some work on it, isn't it? Yes, I've just done some work on it. So either I have done some work on the system or the system has done some work on the surrounding. Even at that point of time, we will be able to change the internal energy. Correct? Yes, we will be able to change the internal energy. But the total energy of the system, my dear student, remains constant. Yes, what did I say? The total energy of the system will remain constant. Yes, 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 yes. Also, what if matter enters or leaves the system? Even at that point of time, we can change the internal energy, isn't it? Yes, we can. So now here comes something that is very important, and this very important point is, everybody star marking it, and remember that total energy of the system remains constant. Okay, what did I say? Total energy of system remains constant. All right, it remains constant. Okay, now this internal energy, right? This internal energy, my dear student, it is, haven't I just told you that heat passes in or out of the system, you will be able to change the internal energy, right? Yes, so that means it is dependent on temperature. Yes, that means that it depends on temperature. Am I right, everybody? Please answer. Tell me, everyone. Yes, 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 guys. I have told you that you can change the internal energy if matter enters or escapes out of the system. If heat gets in or escapes out of the system. If work is done on the system or if it goes out of the system, that point of time internal energy changes. So now tell me, if I say that internal energy is dependent on temperature, would it be right? Yes, thank you so much, Arvind. It will be right for me to say that internal energy depends on temperature. So that means that if there is an isothermal process, what will happen to the internal energy? Isothermal, constant temperature, no heat is passing in, no heat is passing out. That means that delta U, my internal energy change, is also going to be 0. Getting the concepts, everybody? Isn't it easy? Isn't it easy? with this storytelling, I believe that it is very easy. So what did I say? I have just told you, everybody, that U, that is internal energy, depends on temperature. Depends on temperature. If there is isothermal process, if there is an isothermal process, then what will happen? If there is an isothermal process, delta U, that is the change in the internal energy, is going to be zero, because isothermal process is what? Isothermal process means that temperature is constant, right, everybody? Great. Okay. Now you have to understand one more thing. When is this internal energy going to be negative, and when is this internal energy going to be positive? Yo, everybody, I believe that this is very easy concept, everybody. Yes. Okay. If I release energy, let's consider that I am the system. If I release energy, bole to, what if I spend my money? The moment I spend my money, what is happening? My bank balance is going tick 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 tick, beep, 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 it's going down, it's going down, it's going down, it's going down, right? Negative. Why? Because when I spend money, it is from my bank balance that the money is going. So negative, delta U can be negative. But if let's say that tomorrow, let's say that my, my aunt and uncle and everybody, they come. If they come, every time I touch their feet, I'll get some money. It will be great, no? Even if my, even if my back pains a little bit, I think I will still touch their feet. Why? Because I'll be getting some money. Why? At that point of time, internal energy is going to be positive, because my bank balance is increasing at that point of time. Do you guys understand, everyone? So do we understand this? I think now you won't forget it. The fact that ma'am's back pains, and yet ma'am is going to touch their feet only because I get some money, I think you will remember it, right? So everybody, what is the moral of the story from this chapter? Moral of the story is you should touch your elders' feet because you get money. Because you get money, everybody. Yes, so that's why you touch the feet. Oh, please do not show this video to any of your don't show it to your parents and all. Yeah, you show it to your parents, I think all of us will, they will say, oh, this teacher teaches you, that is why you're like that. Okay, so don't show this to any of your elderly people. Do not show it to them. All right, so everybody, coming back to it, what did I say? I said that yes, energy released by system, energy released by system, that means delta U negative. And if energy is absorbed by system, then what will happen? Energy absorbed by system, delta U is equal to positive. Yes, someone is writing some answers related to your work done. We will come to that, don't worry, we will come to that work done and everything. But right now, do you understand what I spoke about internal energy? You do, right? Yes. And we have also spoken about how in isothermal processes, delta U is going to be 0, right, everybody? Amazing, very good. You already get envelopes. Yes, that's it. No. No. No, someone, you don't take it seriously. Yeah, it was just a joke, and only so that you guys remember what I'm telling you. Yeah, it's just a joke. I also respect my elders, and so should you. We must respect our elders. Yeah, and don't ask me to recommend anything. I'm not going to do that. It's a joke. Chill. Alright guys, now we're going to talk about internal energy change by work. Yes, what are we going to talk about? We're going to talk about internal energy change by work. Now we come to something that is related to our work done. Shall we? Chalo. Yes, now we are going to talk about internal energy change by work. Internal energy change by work. Let's do that. Yep. Let us do that, everybody. Now let us suppose, okay, how long will this session go? I have no idea. Whenever it finishes, we will finish it. Yeah. If not, then I will take it tomorrow or day after again. Don't worry about it. Yeah. Okay. Sure. So everybody, let us imagine that we take an adiabatic system. In case of an adiabatic system, what happens, bachos? Everybody, do you remember? In case of an adiabatic system, there is no allowance of transfer of energy. Yes, you are not going to transfer any sort of energy when it comes to an adiabatic wall. But in an adiabatic wall, bachos, what is allowed is matter, or what is allowed is work. That is allowed to you. But energy transfer as heat is not allowed to you when you have an adiabatic wall. And I am saying that if we are taking an adiabatic system, so if we take an adiabatic system, how can you change the internal energy? How can you change the internal energy? What is it that you can do to change the internal energy? For you to be able to change the internal energy, either you can apply some electric work, right? Can you not do some electric work? Yes, I can do. I'm not going to, it is an adiabatic system, so I cannot just give it some heat, right? I cannot do that. But I can definitely, what I can do is I can definitely bring an immersion rod and dip it inside and switch it on. Then what will happen? Electric work. I'm not doing the work. Electric work, done. But there is also a possibility that I can do the work. Remember, sometime back only I took this copper glass and what did I do? I stirred it. When I stirred it, what is this? This is a mechanical work. This is a mechanical work. I used the stirrer. So what I can do is, how can I change internal energy? By doing some mechanical work, by using a stirrer. Or what I can do is, I can bring an immersion rod and I can just dip it in, and that way also, yes, internal energy will change. Because immersion rod will change the temperature, it will change the heat energy, the water molecules or whatever is present there, it will gain some energy and the internal energy will change. Am I right, everybody? Am I right, guys? Yes, yes, everybody. Do we understand this? Do we understand this, guys? Yes or no? Do you understand this? Rama Devi, I'm so sorry if you're struggling in organic reactions. No worries. Please watch Pahul sir's video. He is the one who's taking care of organic and he will be able to help you. Yes. Do we understand this, everybody? That if we have, let's say that, what did I say? I just told you that, let's say that we have an adiabatic system, right? We have an adiabatic system, and in an adiabatic system, how can we change the internal energy? We can do so by, one, doing some electrical work. Yes, by doing some electric work, right? Or what I can do is mechanical work. Am I right, guys? By doing some mechanical work. So we can do either of the two. Great. Okay. Now, in both the cases, bachos, we have to understand that the state of the system is same. The state of the system is same. I am not changing the state at all. Yes, and we have to understand that regardless of whatever path I have taken, either I have taken the mechanical work path or I have taken the electrical work path, it does not matter. It does not matter that what path I have taken to change the state, but in both the cases, my change in state of the system is same. Am I making sense, everybody? Am I making sense, everyone? So right here, everybody, because my change in state of the system is same regardless of whatever path I have taken. So can I say that delta U here is equal to the adiabatic work? Whatever work I have done, either I have done the mechanical work or I have done the electrical work, it does not matter. Can I just say that because my state of the system remains same, so can I say that delta U, which is your change in internal energy, is equal to adiabatic work? Can I say that, everybody? Tell me yes or no. Can I say that? I can say that. Am I right? I can say that, isn't it? Yes, I can say that, right? Very good. Very good. Very good. Okay. All right, guys. Now moving on, let us understand that what is adiabatic work. Yes, let us understand what is adiabatic work. What is your adiabatic work, everybody? Guys, please pay attention, okay? Adiabatic work, how do I denote it? I can denote it as WAD, isn't it? I can denote it as WAD. Can I do that? Can I do that? Yes. All right. Now, if by chance this adiabatic work, if it is positive, that means that, what does it mean? If this work done is positive, then what does this mean? This means that somebody was telling. Yes, do you remember? Somebody told me that, ma'am, that is because work done is on the system. Very good. That means that work done on the system. Work done on the system. Am I right? But if work done by the system, if the work done is by the system, then what will happen? Work done is by the system, then we will say that it is going to be negative, right? It is going to be negative. Am I right, everybody? Am I right, guys? Yes. So till here, do we understand everything? Till here, do we understand everything, guys? Please tell me. Yes. Is it hashtag EPBT? Hashtag EPBT means easy peasy biryani tasty. Till now, whatever I have said, does it seem like it is easy peasy biryani tasty? Everybody, please quickly go ahead and let me know. Yes, go ahead, guys. Let me know, everybody. Till then, I'm going to drink some water, and so should you. Please hydrate yourself and please tell me. Yes, please tell me, guys, everybody. Is it easy peasy biryani tasty, everyone? Yes? Chalo. Very good. Easy peasy biryani tasty. We understand. Awesome. Okay. Now, guys, let us try to understand. Okay. Let us try to understand internal energy change by heat. We have just understood internal energy change by work. Now, let's understand internal energy change by heat. Okay. Internal energy change by heat. Chalo. Let us do that. Now let's say that we have a system, okay? But this time we do not have an adiabatic wall, all right, everybody? This time we do not have an adiabatic wall, but we have rather a thermally conducting wall. Once again, bringing to you my copper glass today. So everybody, we all know that copper, right? It's metal is conducting, metal is conducting. So that means that this is a thermally conducting wall. You don't have to imagine. You understand that this glass is going to have thermally conducting wall. In this thermally conducting wall, everybody, I understand that matter can be taken in or out, and I can understand that there is also energy that is getting exchanged here, right? There is also energy that is getting exchanged here. So at this point of time, everybody, we have to understand. Please try and understand, guys. Please try and understand. Pay attention, everybody. Please pay attention, guys. Do not go ahead of yourself that, ma'am, do this kind of question. Ma'am, how many questions? Ma'am, how much time will you take? Don't. Sit and study, no? I'm explaining. Chill. I'll tell you everything. For everything, there will be time, but right now, pay attention to what I'm teaching. All right? Yes. We are going to solve questions as well. And by the way, I have recently done a session, right? Day before yesterday, I had done a session on redox and thermodynamics, isn't it? So yes, there were questions that I have done. So chill, Mari, wait up, hold on and listen. So the internal energy right here, U of the system may change. When? When the work is done on the system or by the system, which we have just looked at, right? Now I'm saying that we have a thermally conducting wall. If it is a thermally conducting wall, everybody, so heat can pass in or out of the system. Matter can leave in or out of the system, isn't it? Matter can leave in or out of the system. Heat can pass in or out of the system. So that means, everybody, I can definitely say that right here, my internal energy is equal to Q. What is Q? Q is the heat transferred due to difference in energy. What is Q? Q is, everyone, Q is heat transferred. Q is heat transferred, yes, due to difference in energy. Due to difference in energy. Am I making myself clear, everybody? I have just told you this is a thermally conducting wall. Yes, this is a thermally conducting wall. And here heat is getting transferred because of the difference in energy. But where is this difference in energy coming in? You have to understand that, imagine this is a glass, this is my system, right? This system has a thermally conducting wall, right, where energy and matter both can get exchanged. And imagine if I take this and if I put it in a reservoir. Now what if I have a reservoir where I have temperature which is equal to T2 and this is at constant volume? Now what will happen? Now what will happen? So this particular glass has a temperature which is T1, and if I say that I have kept whole of these in a reservoir, this is my reservoir, okay? No, wait. I think I can explain this to you a little better if I take another example. I think, okay, yeah. So I have this glass, which is my system. This is a temperature T1, okay? This is a temperature T1, all right? And now imagine this is my reservoir and this reservoir is a temperature T2. So now if I keep it like this, now this temperature which is a T2 and this temperature which is a T1, there will be some amount of heat exchange that will happen. There will be some amount of heat exchange that will happen, and that is exactly what I have written. I have written that heat transfer due to difference in energy. Heat transfer due to difference in energy. So everybody, now are we clear what I just explained to you? Yes. Did we understand? Yes. Now what I'm saying is that Q is negative when heat is transferred from the system to the surrounding. When is Q negative? From this glass, if it goes to the surrounding, then Q is negative. But if from the surrounding it is absorbing the heat, then it is going to be positive. Right, everybody? Right, guys? Is this all clear, everyone? Is this all clear? Yes. Now, bachos, so we have understood that delta U is equal to Q. But we have also seen that delta U is equal to the adiabatic work, which I can write it as W, isn't it? I can. So now if somebody asks me, now let's say that someone is asking me, okay, where are we? Okay. Now if somebody asks me, bachos, that what is internal energy change by heat and work? What is internal energy change by heat and work? What am I going to say? What am I going to say, everybody? Somebody is asking me internal energy change by heat and work, okay? By heat and work. Now what am I going to say? So we just have to combine these two last equations that we have studied, and from here we will understand that, oh, what is ma'am trying to say? What is ma'am trying to say, everybody? Now we can understand that delta U is equal to Q plus W, where Q is a path function, W is a path function, but do you remember that delta U is a state function? This is a state function, but these two are, my dear students, path function. Isn't it nice that, just like how negative and negative makes it positive, here two path functions together are giving you a state function. And what is this? And what is this? Is there anybody who can tell me in the chat box that what is this? What is it that we have just understood, bachos? What is it that we have just understood, everybody? What is it that we have just understood right here, right now? What is this equation? This equation, internal energy change by heat and work. What is this? This, my dear students, is everybody. This is your first law of thermodynamics. What is this? This is your first law of thermodynamics, right? Haven't you studied? Energy cannot be created, energy cannot be destroyed. Yes, energy can be only transferred from one form to another. Yes, that is exactly what it is. First law of thermodynamics. This is your first law of thermodynamics. Yes. And now we are saying, very good, very good. Navrata has told me, yes. Trisha has told me, very, very, very good, everybody. Very good. Thank you. Thank you, Chandrasekhar. Thank you so much. Yes. Now, the energy of this isolated system is constant. Why? Law of conservation of energy. Haven't we learned about this? That is your first law of thermodynamics, right? Energy cannot be created, energy cannot be destroyed, energy can be only transferred from one form to another. What does it mean? It means law of conservation of energy, because energy of an isolated system is constant, isn't it? Yes. Are we having fun, guys? Are we understanding all of these, everything and anything that I'm telling you? Are we understanding this? Please keep writing hashtag EPBT so that I understand. So what am I writing here? I'm writing that the energy of an isolated, why did I write off? No off. See, I'm very absent-minded here. You disturb me for a second and I'm gone. My mind is gone somewhere else, okay? So the energy of an isolated system. What is isolated system? You know what is isolated system. Energy of an isolated system is a constant. Why? Law of conservation of energy. This is law of conservation of energy. Yes, so do we understand this, guys? Do we understand this? Yes, guys? Yes, everybody? We understand this? Cool. Cool. All right. Yes. Now, do I see hashtag EPBT? Do I see hashtag EPBT? Yeah, thank God. You guys are super sweet, yeah. You guys are super sweet, everybody. Chalo. Now, are we ready to do some questions? Shall we do some questions, everybody? Yes? Shall we do some question, guys? Let's do that. Chalo. Here are some questions bringing to you. So we are done with this, guys. First law of thermodynamics. I've just explained to you law of energy of conservation. This law states that energy cannot be created or destroyed, only gets converted from one form to another. This is something that you have learned from your childhood, isn't it? Everybody knows that, isn't it? And what is it? It is delta U. So delta U means what? Internal energy change. That means what? There is a final state and there is an initial state. So U2 is final, U1 is initial. So U2 minus U1, you can write that, and that is equal to Q plus W. All right, yes. Then we also read about the sign convention of work, haven't I? If internal, see, heat is absorbed by the system, from the surrounding, positive. Heat is given by the system to the surrounding, negative. Work done on the system, it is positive. Work done by the system, it is negative. Right, everybody? Yes. Do we understand this? Clear? Great. Awesome. So now, here we have a question. Our first question, everybody, is, a system is changed from state A to state B by one path and from B to A by another path. The question is, if delta E1 and delta E2 are the corresponding changes in internal energy, then what is the option that we are looking at? Anybody? Anybody who can tell me this? Look at the question. What does the question say? The question says that internal energy. You know what? You don't even have to read the question twice. The question says that a system is changed from state A to state B by one path and from B to A by another path. Delta E1 is internal energy for the first one and delta E2 is the internal energy for the second path. But what do we know? Don't we know that internal energy is a state function? Who cares what path you are taking? I've just told you. Internal energy is a state function, bachos. Who cares what path you are taking? So that means that because you started from A, you went to B and you came back to A, your internal energy is going to be 0. Right? Because you came back to the starting state of A, it is going to be 0. So E1 plus E2 is equal to 0. That means option C is the correct answer. Tricky but easy, isn't it? See? Hey, Brooklyn. So all this time you were asking me about cyclic processes, isn't it? This is not a cyclic process because here we do not have a loop. But this is somewhat related to it because in JEE you might see certain bit of tricky questions like this. Yes. The correct answer is, it is 0. E1 plus E2 is equal to 0. Yes. E1 plus E2 is equal to 0. Very good, everybody. Very good. Yes. Guys, by the way, I can see one thing, that none of you have liked this session, huh? And you are also not telling your friends about it. Why so? Huh? Why so none of you are telling your friends about this, but otherwise we are still putting in effort and you guys are not putting efforts for us. You must tell your friends. Yes, you must share it with your friends that in Vedantu JEE English we are taking a lot of sessions. Anyway, chalo guys. Moving on to the next question, everybody. The next question is, gas in a container absorbs 300 joules of heat. And after this, 100 joule of work is done on it, which is followed by 50 joules of work done by the gas. The increase in the internal energy of the gas is. Chalo, okay, very good. Creo King, that's an amazing song, yeah, whatever you are singing. All that chippy chippa, whatever you are singing, very good, very good. Okay, guys, let us try to solve this. Yes, so what do we have? What do we have, everybody? We have amount of heat absorbed, right? Yes, amount of heat absorbed. Amount of heat absorbed, everybody, is equal to 300 joules. Now, this is going to be positive, right? Because heat is absorbed. Heat is absorbed, so that means that it is plus 300 joule. Heat is absorbed, bole to can I write this as Q? Because heat is absorbed, right, from the surrounding. So Q, great, yes. Now, what is work done by gas? The work done by gas is equal to, work done by gas is equal to W, let's say, and this W is equal to, initially, the work is done on it. The work is done by the gas, right? The work is done by the gas, so it is going to be 100. And then, no, the work is done on the gas and then it is done by the gas, so minus 50. So that means we will have 50 joule, right? Yes, okay. Now what do we have? We know that Q is equal to delta U plus W, or delta U is equal to Q plus W from the first law of thermodynamics, isn't it? Yes, from the first law of thermodynamics we have Q is equal to delta U plus W, great, okay. So that means that what do we have? We have 300 is equal to delta U plus 50. That means that it is going to be 350 joule, isn't it? It is going to be 350 joule. I hope I'm right. Am I not right, guys? Delta U is equal to Q plus W, isn't it? Yeah, why do we have to do that? This also. Delta U is equal to Q plus W. So Q is your 300 and plus W is equal to 50. So all you have to do is, the answer is 350 joules. Very good. See? It is 350 joules. Very good. Absolutely right, everybody. Are we done with this, guys? Are we done with this? Yes, we are. All right. Let's go to the next question. Let's go to the next question. This was also easy peasy biryani tasty. Next question. See, this next question has come in your 2019. Guys, could you give me one moment? I just have to go to the washroom. Yeah? Could you give me one moment? I'll just have to go to the washroom and come back. Yeah? Till then, try and solve this question. Okay? Try and solve this question. I'll be back, guys. I'll be back. All right, guys. I'm back. Yeah. C. Some people are saying C, some people are saying B. All right, let's see. I haven't read the question. Let's read the question. During compression of a spring, the work is done is 10 kilojoule and 2 kilojoule escaped to the surroundings as heat. Okay. What is the change in the internal energy? So, bachos, what is given to you is that Q is equal to minus 2 kilojoule, because it escaped out, right? That means that it had to be done by the system. Very good. And we can also see that the work done is equal to 10 kilojoule. Am I right? Yes, very good. Now what do we know? We know that delta U is equal to Q plus W. So that means that 10 and plus minus, or plus minus 2. That means that it is going to be 8 kilojoule, everybody. 8 kilojoule. So that means option C. And now everybody tell me something. Just look at this. This question has come in your JEE 2019. This question has come in your JEE 2019, everybody. This question has come in JEE 2019. Can you believe it? What an easy peasy question this is. This is super easy question, isn't it? What an easy question this is. Won't you be very happy if you look at this question? Yeah? Won't you be very happy if you look at this question, everybody? I think you will be. I think you will be, right? भारत का बच्चा बच्चा क्या बोलेगा? What do I know? क्या बोलेगा? क्या बोलेगा? It is a JEE question. I'm not kidding. You can go look for it. You can go look for it. This is a JEE 2019 question. This is a chemistry question. Chemistry. Change in internal energy, they are saying, na? Hey, Brooklyn, what am I teaching you? Chemistry. Why will I teach you a physics question? Huh? Why will I teach you a physics question? This is a chemistry question only. Arre bhag, Hazarika facts, Hindi it seems. In an educational class, you are talking about religious. We don't go there. We don't go there. All of that is my personal belief, and I'm not going to say all of these things in my classes. So please stay quiet and study, or don't study, but do not disturb the class with these things. Okay? Yeah, exactly. This has come last year. This 2019. It has come. But anyway, JEE mains mein you will see a lot of questions like this. There will be a lot of easy questions, but you will just get surprised that, hey, this happened really? This happened really? It'll be surprising. Chalo. Anyway, guys, we are done with few questions. Now, shall we continue? Let us continue with something that is called as pressure volume work. Okay. Everybody, do you remember when I was, the last time when I took this session, last time when I took thermodynamics, you know, I had a piston, everybody. I had a piston. But now I believe I do not have the piston, everyone. I do not have the piston. But chalo, let us try and understand this. So imagine that we have a pen here, okay? Thank you, Moni. Thank you so much. Thank you so much. Can you give 2023 PYQ? Sanjeev, did you not see? Very recently, I had taken you through questions now. Okay, I think you guys are not watching our channel very well. Okay, have a look, everybody. Have a look, guys. This is our Vedantu JEE English channel. Okay, this is our Vedantu JEE English channel. Where am I? Where am I? Where am I? So let me tell. This is our Vedantu JEE English channel. All right, bachos. Now in this channel, if you go here, right here, you will see that I have taken. Acha, this was electrochemistry and redox. So for thermodynamics, I believe I'll do a PYQ. Okay. I think I'll do a PYQ for thermodynamics later on, or I will give you the PYQs. Don't worry about it. Chalo. All right. Okay, guys, let us understand delta U, that is internal energy change by pressure volume work. Okay. What is this pressure volume work? Let us try to understand. Let's say that, imagine this is a piston. Okay. Imagine this is a piston. Okay. Piston, you know, that injection wala piston, everybody knows. Yes, great. Okay. So if I want to press this piston slowly, or if I just do this, see, one click, the process is happening, right? One click, the process is happening. Okay. So now what is happening is, everybody try and imagine and understand, please. Okay. Yes, try and imagine and understand. Okay. Everybody listen. What am I saying? I'm saying pressure volume work done. Okay. Pressure volume work done. When do you think this pressure and volume work will be done? When do you think this pressure and volume work will be done? So imagine if this is not a pen, but if this was a piston. So don't you think that if inside there is a gas, if the gas expands, then this piston will go out? And if the gas compresses, then this piston will go in like this? Yes or no? Yes or no, everybody? Yes or no, guys? Are you understanding? Chalo, let me draw this and try to explain this to you. So imagine that you have a piston here like this, okay? You have a piston here like this. And let's say that here, okay? Here. This is where you are going to press. So let's say that this is your initial volume, and when and when you bring the piston here, let's say now you bring the piston here, then what will happen to the volume? This is your final volume, right? This is your final volume. So when you are compressing the gas, then what is happening? The work is done on the system, right? The work is done on the system. But if the gas expands, then the volume is going to expand, isn't it? The volume is going to expand. Very good. Great. Okay. So that means everybody. Let me write down the heading here. The heading is pressure, volume, work. Pressure, volume, work, right? This is what we are talking about. So in this case, did you understand what I just said? I have just told you that here volume change will happen. So if I write here volume change, that means that I can denote it as delta V, volume change. So can I write it as delta V? I can write it as delta V, right? So my delta V is, how do you give volume? You give volume as L multiplied with area of cross section, isn't it? Length multiplied with area of cross section, isn't it going to be there? Yes. Isn't it going to be there? It is. Vijay, kindly sponsor the board that you are talking about. I do not have that much money. It costs us 5 lakh rupees. Do you have? Give it to me. I'll buy the board. Until you do not have that much money, I don't have that much money. Let's not talk about it and let's get into this, okay? I'm also standing here and I keep walking so that you can see the board. So, bacha, let's please not do that again and again, everybody. Let us understand that I do not have 5 lakh rupees. You do not have 5 lakh rupees either. None of us have it. So, let us study here, okay? All right? Let us study here. Chalo. So, I can write it as delta V. Now my delta V is, how do you give volume, everybody? In mathematically, you all know that it is length into area of cross section. Great. And I can also write that this delta V, I have just spoken to you about Vf and Vi, my final volume and my initial volume. Did you see? I have just spoken to you about it. So I can also write it as V final minus V initial, isn't it? Yes. Great. Acha. Now let us talk about the force on the piston. Force on the piston. If the piston is going inside, that means from the outside the pressure is working on it. Right, everybody? Right, everyone? Because at this point of time, the gas is not expanding. I am pushing the piston, isn't it? Yes. So what is going to be my force on piston? What is going to be my force on piston, everybody? We all know very well that it is going to be pressure multiplied with area, because we know that pressure is equal to force divided by area. This is something that we have learned in 8th or 9th standard, isn't it? Pressure is equal to force by area. That means the force on piston is equal to pressure multiplied with area. And right here I have just told you that this pressure is externally applied. This is applied by me. Who am I? I am not in the system. I am external. So it will be P external multiplied with area. Correct? Making sense, everybody? Great. Okay. So now if I want to write down the work done, let's say I want to find out the work done here, okay? What is going to be my work done? What is going to be my work done, everybody? The work done on system, if I move the piston, everybody, then what is it going to be? It is going to be the force into L. Yes? Yes? What is L? L is the distance covered. L is the distance covered. That is going to be my work done, isn't it, guys? Are you agreeing to it or not? Hello, people. It is going to be force. Are you guys understanding? What is this? It is going to be force multiplied with L. What is L? L is the distance covered by the piston. The piston covered some distance, right? The piston covered some distance. So can we write this? Yes or no? Nobody is saying anything. Bachos, how will I understand if none of you say anything? Yes or no, people? Yes. Thank you so much, Anugna. Great. Yes. So that means I have just figured out that what is my F? My F is equal to P external multiplied with A. Yes, it is P external multiplied with A, and then I can write that it is multiplied with L. I can write that. Now what is A into LC? A into L is delta V, so that means that my P external is multiplied with delta V here. Am I right? Now, bachos, do you remember that my initial volume was more and my final volume is less? My final volume is less because why? Compression. The volume decreased. The piston moved inside. The volume decreased. If this decreases, that means that my delta V is going to be negative. But everybody, remember that work is done on the system. The work is done on the system, bacha. The work is done on the system. If it is on the system, then my work done is supposed to be positive. Am I right? So when do you think I'm going to get a positive value? When my delta V is negative and my external pressure also has to be negative, right? Right, people? So that means, can I write that W is equal to, now instead of writing that my delta V is negative, let me just write minus P delta V when it is getting compressed. When it is getting compressed, can I write that this is my equation? This is my equation when compression is happening. And if I want to speak about expansion, then when it is expanding, then what? Then it is going to be minus W is equal to P delta V, and this is for expansion, bachos. This is for expansion. So now the system is going to work. Hence, for expansion, you write it as this. Achha, now if you remember, just some time back, remember one click it was happening, yes? Do you remember what did I do? I did this, click, 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 click. What is this? This is single step. This is a single step. Understand this, by the way. Now what am I doing? I'm taking one shot, right? In one shot, I'm going to cover JEE Mains questions. I'm going to cover concepts. I'm going to cover tips. I'm going to cover tricks. I'm going to cover the important formulas, everything. Now, if I take a session which is for 3 hours and if I can complete everything versus from the starting of the academic session, every single day, if I taught you single step versus gradual step, internal energy change by work, internal energy change by heat. If one day, every day I took one session of 1 hour, would you have come to my class? You don't. I have seen that. I've done that. Right? When I take chotu lessons, you don't come. You are like, yeah, ma'am will anyway teach, Ma'am will anyway teach, right? Right? It is supposed to be same, but I will tell you about that also. But you will see that there is, you will see that there is. No, expansion and compression, how is it same? No, bacha. Do you see that in case of compression, compression, the work is done on the system. So work has to be positive. When it is expansion, at that time, the work done will be negative, bacha. Sabarna, do you understand? Yes. Okay, now, what do you understand that if I take a session which is single step, like right now, I'm taking one shot and I'm going to finish everything, right? And then, if I take gradually, what is the point of taking, like when we take this one shot crash course, what is a crash course? What is a one shot? It is basically all throughout the 2 years, whatever you had to learn. Yes, throughout 2 years, whatever you had to learn, that we are doing it in one shot. That means that, bachos, I can write it as my W is going to be minus, yes, it is going to be minus integration of VI to VF, that is from volume initial to volume final, P external dV. This will be integration, isn't it? It will be integration, right? This will be integration, am I right? Very good. This is my integration. Very good. Okay. All right, everybody. Great. Okay. Okay. Now, let us understand something that is called, no ma'am, the formulas are similar. Yes, bacha, the formulas are going to be similar only. But what you are not understanding is, see, there is a sign change. Okay. All these while we were talking about sign convention as well. So here, the only difference is the sign convention. That's it. Nothing else. Okay. Yes, the formulas are similar. It's only the sign that will change. That's what I was telling you, right? Work done on the system, work done by the system. That's the difference. Okay? That is the difference. All right. Yes. Won't there be subject-wise cutoff in the JEE main? No, usually not. Subject-wise cutoff is not there. However, I am not very sure. We'll have to figure it out. I have to see that. So I don't want to answer right, okay? So I don't want to answer you right now, but just please pay attention, okay? Alright, please pay attention. Chalo. Now we come across something that is called as reversible and irreversible process. Do you all know what is a reversible process and what is an irreversible process? What is a reversible process? A reversible process is where you can change it back to its original state, isn't it? And what is an irreversible process? When something has happened and after that you cannot bring it back. That is your irreversible process. Now, in this case, we are saying is, in this case, what we are saying is that when, let's say that when you do this single step is irreversible process. But what we do not understand is that the reversible process is gradual change, slowly and steadily, slowly and steadily, slowly and steadily, slowly and steadily, it occurs. Are you getting my point, everybody? So imagine, okay, let's again go back to our cooking class, okay? So in a cooking vessel, okay, we are cooking, let's say we are cooking suddenly. What do you do? What do you do? You take a little bit of salt and then you pour it, right? And then you pour it, isn't it? And sometimes even if the salt, and you taste it and see that is the salt more, is the salt less, right? If it seems like it is a little bit more, then you add a little bit of water. If it does not seem like it is a lot, then you just let it go, right? But do you, everybody, do you in single step, do you bring the whole jar of salt and just pour it? Like one single step, I want it to be done. Do you do that? Do you do that? You don't do that. And if in one single step you pour the whole salt, everybody, yes, if in the whole lot, if you pour the whole salt, everybody, will you be able to change it? No, this becomes irreversible. Single step, irreversible, the damage is done, you won't be able to eat the food. But reversible, if you just put a little bit of salt, then what will happen? After some time you can change it, right? You can add some water and you can bring the taste to usual, right? Yes, if you don't like the taste, you like it like that, it is fine, isn't it? So do you understand this difference, everybody? Do you understand this difference, everyone, guys? Yes? Yes or no? Yes or no? Is it EPBT? Do you understand what is reversible and irreversible I'm saying? So I am saying that in irreversible process, single step, okay? Now, let us understand that in a reversible process, how the work done is going to look like, okay? How the work done is going to look like in case of a reversible process. So, I'm going to write it here. W reversible is equal to, everybody, it is again going to be -1 integration. Let's say V1 is our V initial and V2 is our volume final. And here we have P external multiplied with dV, okay? Now you know integration, but I do not know so much of integration. So here again it will be minus. Yes, minus integration. Let's say V1 to V2. And here let us just say that every time in a reversible process, everybody, in a reversible process, every time the pressure is changing slightly, isn't it? The pressure is not capital P. How is the pressure changing? It is only changing by plus minus dP, which is a small amount, right? So can I write it like this? P plus minus dP multiplied with dV. It's a reversible process. So it's only changing slightly. So plus minus dP. Can I write it? I can write it. Now bachus, you tell me, so it will be P multiplied with dV and it will be plus minus dP multiplied with dV. Now dP and dV, both of them are infinitesimal small terms, isn't it? So if I multiply them, it will still remain small and I can negate it. I cannot consider it at all. I can think that this is negligible. So what I can do is I will write it as V1 to V2 integration and I will write it as PdV. Do you understand? Do you understand, everybody? Do you guys understand? Yes, yes we do, right? Now, do you remember, everybody, we have learned a gas equation, isn't it? We have learned an ideal gas equation. What is that ideal gas equation? P is equal to nRT by V. What do we know? we know that PV is equal to nRT, or you can say that P is equal to nRT by V. Correct. So from this equation, now I can say that my work done in a reversible process is equal to V1 to V2 here minus, and I can write it as nRT divided by capital V multiplied with dV. Can I write it like this? Yes, I can. Now we can clearly see that, everybody, we can clearly see that nRT is what? It's all constant. And because it is all constant, I will take this out of the integration, and I will keep this as V1 to V2. Here it will be 1 by V multiplied with dV. Am I right? Am I right, everybody? Yes, guys. Very good, Arvind. Very good, Rimpi. Well done, everybody. Do we understand this? This much is clear, guys? This much integration is all clear to you? Yes? Yes? Do we understand this much? EPB2? EPB2 it seems. EPBT, everybody? Yes? Okay, great. Acha, now you must have also learned about something that is like minus nRT. Do you remember ln of V we use? We use natural log of V, right? 1 by V, integration of 1 by V. So what will I write? I will write here ln of V, and right here is my limits V1 to V2. So that means that I can still write it as minus nRT. Yes, ln of V2 minus ln V1, isn't it? Yes, I can do that. And once I have done that, now I can write it as minus nRT ln V2 by V1. Logarithm operations, right? You all know this. Now, because I have a natural log, I want to change it to log. What will I do? Hey, simple, 2.303 RT log V2 by V1. Whenever you want to change natural log to your log, you will do what? You will multiply it with minus 2.303 n, minus 2.303. Okay. All right, everybody. Oh, n missed. I missed n. Minus 2.303 nRT log V2 by V1. And that, my dear students, is your work done in a reversible process. Gotcha? Yes, everybody. Do you understand this? Do we understand this, guys? Is this clear? Yes? So that means, acha, now remember I was telling you that what will happen if I take like every day 1 hour class instead of taking a complete 3 to 4 hours. This is why I was telling, because if we want to draw the graph, yes, in a graphical representation, we see that a reversible expansion will require more work than irreversible expansion. Okay. All right. Why so? Because the graph looks like this. Okay. The graph looks like this, everybody. Have a look. The graph looks like this. So you draw the graph like this, draw the graph like this, okay? Then what happens? Consider this to be your V1 and consider this place to be your V2, okay? Now let's say that here is your P2 and here somewhere is your P1, okay? Now if I draw the graph, let's say that it comes like this, okay? So what do you see? One step, everybody. If it is one step, guys, then what will happen? Tuck. At one single point, the pressure dips. At one single point, the pressure dips, and at this point of time, your area under the curve will be just this shaded part. All right? All right, everybody? Yes. But if I do a reversible process slowly and steadily, so P to P2, from P1 to P2, if you have to come step by step, everybody. You have to come how? Step by step, and at that point of time, your area under the curve will be this blue shaded part as well as the yellow shaded part, and that is why I said that your area under the curve, which represents the work done, it will be more in case of a reversible expansion. It will be less in case of an irreversible expansion. Guys, am I clear, everyone? Am I clear? Do we understand this? Shall we move forward, everyone? Do we have EPBT, guys? Do we have EPBT? Do we have EPBT, guys? Yes or no? Yes or no? Yes or no? Hello, people. Do we understand all of these things? Or no? Do we understand these things? Or no, guys? Come on. Let me know, people. EPBT? Could you explain it again? EPBT means easy peasy biryani, tasty. Okay. All right. Who was it? Arvind. Arvind, you understand that? Listen to me. So, in the whole 2 years, every single day, if I take 1 hour, one class related to thermodynamics, is going to cost me a lot of work done, isn't it? Yes. But when in one single day, I complete the whole chapter, I complete the tips and tricks, I complete the formulas, I complete the problems, everything. Don't you think that it will be easier for me? Yes, it will be. So now, once again, when I'm telling you, try to understand this, that if I say that it is irreversible, if it is irreversible, so at one single point, yes, and in one click, it will come from P1 to P2, right? It will come P1 to P2. At this point of time, your area under the curve will look like this, just this yellow shaded part. Yes, it will be just this yellow shaded part. But now, when I'm saying that at every single step, right, at every single step, it is a gradual process, then what will happen? It will be, so what you're not understanding is P1 to P2, when it is a gradual process, it is going like this, and at that point of time, this whole thing is going to be your area under the curve. Now do you understand? Now do you understand? Yes. So when it is a reversible process, the whole part, everybody, this whole thing is going to be your area under the curve. But when it is irreversible, it's only this part that is your area under the curve. No, now do you understand? Now could you grasp it? Yes? Now could you grasp it? Yes, you did? Yes, you did? Or no? Yes, thank you. Thank you so much. All right, chalo. Moving on, everybody. Now let's understand work done in free expansion of gas. Okay, what do we understand? We try to understand work done in free expansion of gas. Okay, yes, thank you so much, so when we're saying that work done in free expansion of gas, what is this free expansion? Free expansion means the gas is expanding, but outside there is no pressure external, there is no external pressure. That means that what do we have? Vacuum. When there is vacuum, there is no air molecule outside. So pressure external is equal to 0. And that means that the gas is expanding freely, right? Right to everybody. So can I write it as P external is equal to 0 because vacuum external pressure is going to be 0. Now, if P external is equal to 0, my bachus, you tell me what is work done. Work done is equal to minus P external multiplied with del V. Now, if P external is equal to 0, don't you think that my whole term of work done is equal to 0? It is going to be 0, right? It is going to be 0. So, work done in free expansion of gas is equal to 0, right? Everybody, yes. Now, what is going to become to my first law, everyone? You tell me what is going to become to my first law. My first law, everyone, is delta U is equal to Q plus W. But I am saying that this Q term, it is equal to 0 already. So that means that delta U is equal to Q. Can I say this? Yes, that means constant volume. At constant volume, delta U is equal to Q. Yes, delta U is equal to Q, everybody. All right. Yes, do you understand this? Great. What is delta U? Your delta U, everybody, is U2 minus U1. So U2 minus U1 is equal to Q plus W, where U2 is your internal energy at final state, U1 is internal energy at initial state, Q is amount of heat given to it, and W is amount of work done on it. Great. Okay. Now, everybody, let's understand that for an isothermal change, what will happen in an isothermal change, everyone? Do you remember what we have already discussed? For isothermal change, for isothermal change, what is it? delta U is equal to 0. Do you remember? Internal energy change is going to be 0. Yes. Why? Why? Once again, let's come back to it. Particles movement is dependent on temperature. But I am saying that this is isothermal. That means there is no energy change. That means there is no temperature change. If there is no energy change, no temperature change, then how will you see that there is any internal change that is happening, internal energy change that is happening? There will be none whatsoever. Yes, there will be none. Great. Now moving on, we have to understand that first law equation for isothermal reversible and irreversible changes. Shall we? Shall we? Acha, here reversible and irreversible is written. We will have to do this expansion formula. Yeah, acha, I think I've taken you this. No, I will take you through this. Don't worry. I will take you through this. Yeah, I will take you through this. But now I need some more space. Delta T is equal. Yes, Tamashri, you are right, bacha. You are right. Absolutely right. Chalo, I have added some more page and now we will get back to it, everybody. Now, what did I say? Now we are going to study first law equation for isothermal reversible and irreversible process. Okay? First law equation for isothermal reversible and irreversible changes. So what is this? Now for isothermal change, everybody, once again, we know that is this space enough? Which space is enough? Which space is enough? I didn't get you. Please tell me. Okay. So first of all, we all know that isothermal change, right? For isothermal change, what do we have? We know that delta U is equal to 0, isn't it? For isothermal change, what do we know? We know that delta U is equal to 0. Great. Yes. Now for isothermal irreversible change, everybody. For isothermal irreversible change. For isothermal irreversible change, what will happen, everyone? Do you remember? Do you remember what will happen? You remember that Q is equal to minus W, which is equal to P external multiplied with V final minus VI. That is delta V. Delta V basically, right? So for isothermal reversible change, yes, for isothermal, achha, that is done. For isothermal reversible change, what will happen, bachos? We will have Q is equal to minus W and we know that it is equal to nRT ln of Vf by Vi, isn't it? Which is equal to 2.303 nRT log Vf by Vi, isn't it? Minus a minus. Correct, everybody? Is this right, guys? Is this right? Yes. Very good, Tamashri. Very good. Looks like you are able to understand everything. Now, for an adiabatic change, we know that Q is equal to 0. That means delta U is equal to WAD. What is AD? AD is work done in adiabatic change, right? Right, everybody? What did I say? I said that for adiabatic change, isothermal change we have understood. For an adiabatic change, bachos, for an adiabatic change also, we know that there is no transfer of matter or energy, isn't it? There is no transfer of energy, sorry, matter, yes. No transfer of energy at all. So, Q is equal to 0. If Q is equal to 0, that means that delta U is equal to WAD, and this is an important formula. Okay, this is an important formula. Do we understand this, guys? Yes, yes, yes. So now, finally, we come across another state function. Yes, now that we are all done with it, yes, delta U is equal to WAD. Yes, you are absolutely right, Tomashri, you are absolutely right. Now we come across another state function. So all these while we were talking about internal energy, which is a state function. But now we have to get introduced to another state function, which, my dear student, is, can anybody guess? It is going to be enthalpy. What are we going to talk about? We're going to talk about enthalpy, everybody. So what is this enthalpy? What is this enthalpy? So you have to understand that why are we even talking about enthalpy? We were talking about internal energy. It was going fine, right? It was going pretty cool. We were understanding everything and we kept writing also, ma'am, EPBT. Yes, it was very easy. It was very easy. But why are we introducing another term? Because what we did not what we are not understanding is that on this earth, whatever experiments you take, yes, whatever experiments you are doing, you are conducting, you have to understand that the pressure on top of your head is the same. I told you that. Yes, the pressure on top of your head is the same. So whatever is happening, you are breathing, same pressure. Cooking, same pressure. Taking a bath, same pressure. Yes, the pressure is the same, isn't it? So that means, my dear students, whatever we have studied in this whole thing, we did not consider the fact that, forget about isothermal, it is always constant pressure. That is what we did not consider. And that is why we require a new term, which is enthalpy. So now let's talk about enthalpy, everybody. So we all know, my dear students, what do we know? We all know that delta U is equal to Q plus W, which is our first law. Right? Right. Now, because I'm saying that all of this is happening at constant pressure, everything is happening at constant pressure. So can I write my Q as a QP? Can I write the Q as QP? Because it's constant pressure, I can. And I know that what is W? W is equal to minus P delta V, isn't it? W is equal to minus P delta V, am I right? See, now we are deriving. This is a lot of derivations, everybody. So now I can say that delta U is equal to U2 minus U1, which is equal to QP plus QP, acha chalo, minus, let me write here minus P V2 minus V1, because delta V is what? It is a change in volume. Delta V is what? Basically change in volume, right? So I have written that. Now everybody, let us shuffle this a little bit, okay? Let us shuffle this whole thing a little bit and we will see that what do we get? We get QP is equal to, let us take this U2 minus U1, okay? And I can write it as plus V2 plus V2 minus PV1. Can I do that? I think I can do that. I can do that, right? Great. Now once I do this, what I can do is, let's take all the two terms together and one term together, okay? Then what will I get? I will get it as U2 plus PV2, U2 plus PV2, and I will get minus U1 plus PV1. Can I write it like this? Yes, I can. Yes, I can, everybody. Yes, I can. Okay? All right? Yes, I can. Now, right at this place, do you see? What do you see? You guys are continuously getting U plus PV, and this U plus PV is another term which is denoted as H, which is nothing but your enthalpy, my dear students. So now you can write that your QP is equal to, H2 minus H1, which is nothing but, I can write QP is equal to delta H. Can I do that? QP is equal to delta H. Can I do this? I can do this. And finally, now that we have used delta, now I can also write it as delta H is equal to delta U plus P delta V, and this is another very important term. Works, guys? Everybody, are we understanding this? Please do let me know. Is it easy peasy biryani tasty or is it not, everybody? Do we understand this? Do we understand this, guys? Do we understand this? Yes? HC Verma, enough for chemistry. Re, bachu. If you are asking me this question, then it is definitely not enough for you. Because H.C. Verma is for physics, not for chemistry. For chemistry, you have to read N. Avasthi. For physical chemistry, you read for inorganic only and only NCRT. And for organic, please try and go for O.P. Tandon or Chauhan. Okay? Alright, what are you asking, Bachu? Right now, you are asking me, is H.C. Verma enough for chemistry? Like, seriously? Anyway, is this all clear? Now once again everybody, delta H is negative for an endothermic reaction which evolves heat during the reaction, and delta H is positive when you have, sorry, delta H is negative for an exothermic reaction, okay? Delta H is negative for for an exothermic reaction, and delta H is positive for endothermic reaction, okay? All right? Yes? Okay, done. Acha. Now you might want to ask that, ma'am, what is this delta U and delta H? Isn't internal energy and enthalpy, is this not similar? Okay, so let's try to understand this, everybody. Now you have to understand that these terms, right? These terms, they also somehow are dependent on the volume, right? They're somehow dependent on volume, correct? But do you understand that for solids and liquids, the volume does not really change so much? For solids and liquids, the volume does not change so much. Hence, for solids and liquids, the delta U and delta H actually is similar, you can say. You can say that it is similar. All right. But if we are talking about gases, guys, if we are talking about gases, then we understand that in case of gases, the volume change is a lot, isn't it? Yes, the uh, volume change is a lot. And at that point of time, enthalpy of gases is not going to be same as internal energy. Alright, it becomes significant. So delta H and delta U, it becomes significant when gases are involved, everybody. So shall we move forward and let us take a look at enthalpy of gases, everyone? Let us do that. Chalo. Now we're going to talk about enthalpy related to gases, everyone. Okay, enthalpy for gases, everybody. Let us take a look at this. We will derive another very important formula, everyone. So please pay attention and write it down. Okay, write it down. Now what is our ideal gas equation, everybody? Our ideal gas equation. Chalo, ideal gas equation everybody knows. Before that, let us introduce some terms. Okay, let us say that VA. VA is total volume of gas reactants, okay, total volume on the reactant side, okay. Then let us say that VB, which is total volume of gas on the product side. All right, yes. Now let's say that we have Na. What is Na? Na is number of moles of gas, okay, number of moles of gas reactants. All right, and let us say that we also have Nb, which is number of moles of gas products, now at constant pressure, our ideal gas equation is going to be PVA is equal to NA RT, and on the product side it is going to be PVB, sorry, extremely sorry, one second, it is going to be PVB is equal to NBRT. Am I right, everybody? Yes, yes, absolutely right, isn't it? Absolutely right. So now what I can do is, now I can write it as PVB minus VA is equal to NB minus NA multiplied with RT. Can we write like this, everyone? Yes or no, guys? Yes or no? Can we write it like this? Can we write it like this? Yes or no, guys? Yes, we can. Now from here you understand that this means that P delta V is equal to here NB minus NA. That means this is your delta nRT. Now just to make it a little more, let's just use some of the things that we already know. Now we know that delta U plus P delta V is equal to delta H. Do we not know this? We do know this. So now instead of writing it as P delta V, can I write it as delta H minus delta U is equal to delta nRT. Can I do this? I can do this. And finally, from here, we find a relation which is delta H is equal to delta U plus delta nRT. Now, just to identify that this equation is for gases, we will introduce a term which is G, okay? Delta NGRT. Let us have this equation. This is a very, very, very important equation, everybody, okay? This is a very, very, very important equation, okay? All right. Now we come to some other term that is called as heat capacity, specific heat capacity. Let us understand all of these things fatafat se everyone, okay? What is heat capacity, guys? Or if I have these terms here, then I don't have to write it. Enthalpy of a system, I have already explained to you. Relationship between delta H, second law of thermodynamics, we will come to that. No, it's not there. So I think I will write this down then. Do I have it here? Acha, no. Alright guys, here we go, okay? What is heat capacity? Everybody we have all understood, right? Everybody we have all understood? Great guys. Good to go, right? Good to go. So chalo, let us go to heat capacity. What do you think is heat capacity, everybody? What do you think is your heat capacity? The amount of heat that is required, or we can say that it is absorbed by a system to raise the temperature of a given mass by unit degree. Very good, amazing, Tamashri, very good, amazing. So you know what, I'm not going to spend too much time because these are easy peasy definition and I have already explained to you. So I'm just going to write down the definition so that you have it in your hand and you can correlate this when you are studying. So amount of heat required, or we can say absorbed, yes, absorbed by the system to raise the temperature of a given mass by unit degree is called as your heat capacity, and the formula is Q is equal to C delta T. Okay, this C, my dear student, is your heat capacity. What is the C? The C itself is your heat capacity. Now that we are done with heat capacity, let us also understand what is specific heat capacity, everybody. And what is specific heat capacity? Nothing. Just make it more specific. That's it. Just make it more specific. How do you make it more specific? You write it as quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. All right, that is called as your specific heat capacity. All right guys, yes. Now what is specific heat capacity formula? Specific heat capacity formula is given to you as Q is equal to MC delta T. What is M? M is the mass. M is the mass. All right, yes. Now we have to go through something that is called as the relation between constant pressure and constant volume in an ideal gas. Are we ready, everybody? Are we ready, guys? Yes or no? Yes or no, guys? Are we ready? Yes or no? People, chalo. Now let us try to understand. Everybody. Guys, we only have half an hour or sort of, okay? So let's quickly get done with these, let's quickly get done with these derivations and everything. Chalo. Now what do we have? We have a relation between constant pressure and constant volume in an ideal gas, okay? What did I say? Relation between Cp, constant pressure, and Cv, constant volume, in an ideal gas. What is this? So at constant volume, what do we expect? at constant volume, that is V, yes, what will we have? We will have QV is equal to delta U. Am I right? Yes, delta U. Very good. Now at constant pressure, what am I going to have? I'm going to have QP is equal to delta H. Yes, yes, everybody. All right. Now I know that, or you all know, everybody knows that delta H is equal to delta U plus P delta V, which means now my delta H is equal to QP, so I can write this as QP is equal to QV plus P delta V. Can I do this? Can I do this? Yes, yes, yes. You will go. You will get there. You will get there. Yes, you will get there. Now, for 1 mole ideal gas, okay, for 1 mole ideal gas, what do we have? For 1 mole ideal gas, we have P delta V is equal to R delta T, because PV is equal to nRT and all sort of those things that we know already. Yes, very good. So that means that I can say that QP is equal to QV plus R delta T. Can I do this? I can do this. I can do this. Now, from the heat capacity concept that we have just studied, right? We have studied the heat capacity constant, heat capacity concept. From there, we know that Q is equal to C delta T. Am I right? Absolutely. So that means that my QP is going to be equal to CP delta T, right? Right? Absolutely. Now that I have written that, what does my this equation become? My this equation, what does it become? This equation becomes Cp delta T is equal to Cv delta T plus R delta T. Now that I have so many delta T, what can I do? I can take it as common, isn't it? So Cp delta T is equal to, everybody, Cv plus R multiplied with delta T. Now delta T, I can cancel it out from both LHS and RHS, and what will I get? I will get Cp minus Cv is equal to R. And do you know what this is called as? Do you know what this is called as, everybody? What is this called as? I have removed delta T. Yes, I have removed delta T. Very good. Very good. You guys have understood. Now what is this called as? This is called as Myers relations. Myers relation. Yes, this is called as Myers relation. Okay, this is called as your Myers relation. Myers relation. All right, this is your Myers relation, and it is slightly important for second law and all we will come. Don't worry, second law we will come. There is still time for second law. Chill, chill, chill. Second law and third law is almost at the end. When we do second law and third law, that means that, okay, the chapter is over. It's only the first law that is so much more important, and from the first law you learn, you keep learning. All right? Yes. Okay guys, so now that we are done with this, now we have to understand something that is called as reaction enthalpy. Everybody ready, guys? Are we done with this? We are done with this. Now let us understand reaction enthalpy, but I think that let's do a question before this. Shall we do a question, guys? Are you all with me? Are you all with me or no? That is CPM minus CVM. What is CPM and CVM? What is CPM and CVM? You tell me. Okay, chalo, I will write that down. So Mayer's relation, ideally Mayer's relation is CPM minus CVM is equal to R. This is actually your Mayer's relation. Okay, this is your Mayer's relation, everybody. Now tell me what is CPM and CVM. If you can tell me that, great. What is CPM and CVM? CVM is molar heat capacity at constant volume. Yes. CVM is Molar heat capacity at constant volume. And what is CPM? CPM is molar heat capacity at constant pressure. That's it. That's the only difference. So I hope that you are not too confused. Are you? I hope now you are not too confused. Agreed? Clear? Yes? I will tell you, I will give you those important relations as well. Don't worry about it, okay? I'll give you those important relations as well. But at the end, I'll give you a whole cheat sheet of everything that you require in your exam. Okay? Alright, everybody, shall we move on then? Shall we move on, guys? Yes, Tomashri. How did we do this thing, bacha? See, 1 mole ideal gas, and then we used the heat capacity concept, right? So it is pretty much the same thing. So it is pretty much the same thing, right? Okay, alrighty, everybody. All right. Now, what do we have to understand? Now we have to understand reaction enthalpy. What do we have to understand? Understood, right, Tomashri? Understood, right? Okay, great. Now let us take a look at reaction enthalpy. Chalo. Here we are. Okay. What is reaction enthalpy? Yes. What is reaction enthalpy? The reaction enthalpy is basically that enthalpy change which comes with a reaction. Reaction enthalpy is that enthalpy change which accompanies a reaction or comes along with a reaction, that is called as a reaction enthalpy. Okay. Now I'm not writing this thing. We will do the question. Sorry. We will do the question. But can we do it in some time? In some time, because I have already started with reaction enthalpy. Now again to break. We'll do it in some time. Sorry, yeah. I have started the reaction enthalpy. So let's cover this and then after that we'll do it, okay? After reaction enthalpy, pakka promise we will do it. Chalo. Alright guys, now I'm not writing the definition. I believe that the definition you can find it from your NCERT book. So yes, we will take a look at that later. Now, what is this reaction enthalpy? It is the heat content of the system. That I am going to write it down. Okay. What is it? It is the heat content of the system. Heat content of the system, right? What does it do? It decides. It can decide if the reaction is feasible or not, if the reaction will occur or it won't occur. Yes, that is what a reaction enthalpy does. Now, whenever we have a reaction, right? Let's say that whenever we have a reaction, let's say that we have a reaction sort of A plus B gives us C plus D, right? Let's say that this is our reaction. How do you write the reaction enthalpy? You write the reaction enthalpy, everybody, as delta RH, okay? And what is it? This is sum of enthalpies of products. What do? You write it as sum of enthalpies of product, yes, minus sum of enthalpies of reactants, minus sum of enthalpies of reactants. Okay, so how do we write it? Now I have just given you a simplest form of reaction where small letters are your stoichiometric coefficients and you have reactants, right? So for this particular reaction, we are going to write delta RH. And how do we write it? We will write it as, have a look. You will write it as, yes, small letter C, HC plus DHD. Yes, this is your product. And then subtracting from here, you will write it as AHA plus BH capital B. That's it. This is how you are going to write the reaction enthalpy. Am I clear? Now, reaction enthalpy is not the only form of enthalpy. We have to study some more enthalpy of reaction. Now let us talk about standard enthalpy of reactions. Yes, we have to talk about standard enthalpy of reaction, but before that I think that we should do a question. What do you all say? Yes, now let us do the question. Let us solve the question, everybody. Shall we do that? Shall we do that? Yes or no, guys? Are you all with me or no? Guys, you guys are chatting among yourselves, isn't it? But not talking to me. Chalo, here is your question, guys. Let us have a look at it. Your question is 10 mole of ideal gas expands isothermally and reversibly from a pressure of 10 atm to 1 atm at 300 Kelvin. What is the largest mass which can be lifted through a height of 100 meter? Okay, all right, so chalo, let us have a look at it. What are the things that are given to you? What is given to you is you are given a initial pressure, which is your 10 atmospheric pressure, so 10 atm, right? Then you are given final pressure, which is nothing but 10 atm to 1 atm here. All right, yes. Then you are given T is equal to, temperature is given to you, which is 300 Kelvin, right? Yes. You are given mole, N is equal to 10 mole of ideal gas, that is given to you, right? And we all know that R, capital R is equal to 8.134. Then what is it? Joule Kelvin to the power minus 1 and mole to the power minus 1. And finally, what is given to you? Height, that is given to you as 100 meter. Am I right, everybody? Great. Now let us have a look at it. How do we solve it? So how we solve it is W is equal to, work done is equal to minus 2.303 nRT. Yes, log of P I by PF. We can write it like this. Yes. All right, we can do this. So now we have to calculate, okay? We will calculate minus 2.303 multiplied with N is equal to 10. We know that R is equal to 8.314 or 8.134. 8.134 multiplied with, what is the temperature? Temperature is 300 Kelvin. Yes, now this is log, and I know that Pi is equal to 10 divided by Pf is equal to 1. Now calculate, everybody. This you calculate, and how much will you be getting? This you calculate and tell me how much will you be getting, everybody. Come on. Go, guys. Quick, quick, quick. You can calculate this. Okay, I'm leaving it to you, okay? Whatever answer you get after calculating, now what you are going to get is, so you are going to write the answer, okay? Let's say that this is X. Let's say that this is X. I'm just showing it to you how to solve it. I'm not calculating, okay? Now, let's say that if mass M, okay, if mass M can be lifted by this work done, yes, by this work, yes, through 100 meter height, right? Then what is the formula that I'm going to use? I am going to use work done, W is equal to mgh, isn't it? Now I need to find mass, and my mass is equal to work done divided by G and H. Now work done is the one that we have just figured out here, X, right here. Okay, so all you have to do is put the value of X divided by G is 9.81 meter, S to the power minus 2 multiplied with 100 meter. Calculate this and find out what is the answer. That becomes your answer. Yes, everybody, very good. Work done is equal to mgh. Arey, all that is in physics. Write down in chemistry. Let's make it a little simple. I am not saying that it is potential energy. I'm just saying that it is work done. Why? Because I need work done formula here. Yes, it's not a mistake. I know that in physics you know that that is your potential energy. Here I'm saying that this is my work done. Okay, this is my work that is required for me to lift the mass. Just find this, calculate this, and you will get the answer. What is the answer? Everybody is saying that 58.5. Okay, it must be 58.5 if you are saying. Chalo, I'm not calculating. Oh yeah, you are right. 58.55 kg, that is your answer. 58.55 kg, that is your answer. Chalo guys, okay, it is going on and on. I am also tired now. I don't want to take the class anymore, but I still have to take it, right? Because it's your exam. It's your exam. What to do? It is your exam. Chalo guys, enthalpy of a system and all of these we are done with. Where are more pages? I need more pages. Why do I not have more pages? Didn't I add like a lot of pages here? I do not have pages. 1 second guys, I need more pages, okay? Just a minute. Okay, so we have more questions, but now we are coming back to... Okay, now we're coming back to everybody. Very good, very good. Okay, standard enthalpy of reactions, okay? Yes, now we're coming to standard enthalpy of reaction. So what is the standard enthalpy of reaction and how is it denoted? It is denoted as delta H, and right on top you will have naught, okay? It will be written as delta H naught. So what is the standard enthalpy of reaction? The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states, and also pure form 298 Kelvin, 1 bar atmospheric pressure. 1 bar pressure. Are you getting my point? What did I say? This I will have to write it down just so that you understand, okay? Enthalpy change. Enthalpy change for a reaction when all the participating substances are in their standard states. That is called as standard enthalpy of reaction. Okay, all right, yes. Okay, now we do not only study one, but now we have to study the standard enthalpy of transformations, that is standard enthalpy of fusion, standard enthalpy of vaporization, and standard enthalpy of sublimation. So guys, now I am going to tell you, no break, we only have like half an hour or so, okay? So we have to complete this part. Now, I'm not going to write this because I believe I have provided you with the thermodynamics previous notes. If I have not, don't worry, I will provide you with the notes in the Telegram channel. Background is slightly blur. No. Mohi, can you increase your resolution of the video? Oh my god, it's so cute. It is so cute. Creo King, it's so cute. Chalo. So now guys, I'm going to dictate something. Okay, I'm going to dictate something. Not dictate, I'm just going to tell you, and I will give you the notes later on. Okay, I'll give you the notes. I'll give you my handwritten notes. Don't worry. So first of all, we have standard enthalpy of fusion. What is standard enthalpy of fusion? The enthalpy change that accompanies melting of 1 mole of solid substance in a standard state. Do you understand this? Do you understand this? Yes? Alright. Now, what is standard enthalpy of vaporization? I believe that you know this because you must have studied this in your younger classes, okay? What is it, standard enthalpy of vaporization? Standard enthalpy of vaporization is amount of heat required to vaporize 1 mole of a liquid at standard states, right? Do you get it, everybody? Great. Standard enthalpy of sublimation. What is standard enthalpy of sublimation? The change in enthalpy when 1 mole of a solid substance sublimes at standard state. That's it. Okay. All right. Very good. Now the question that comes in our mind is, after studying all of these, yes, what will be the magnitude of this enthalpy change? What do you think is the number that we will get when enthalpy change occurs? Oh, that depends on intermolecular reactions. That depends on intermolecular interactions. If the intermolecular interactions are too much, then maybe the magnitude will be more. If the intermolecular interactions are less, then maybe the magnitude of enthalpy will be less. Okay. All right. Are we done? No, we are not done yet. We still have to learn about something that is called as standard enthalpy of formation. What is standard enthalpy of formation? This is slightly important. This I will have to write it down. Okay. This we are going to write it down. Everybody with me? Write it down. Standard enthalpy of formation. Standard enthalpy of formation. Okay. What is this? Standard enthalpy change for the formation of 1 mole of a compound from the elements in their reference state, guys. In their reference state. Did you understand? Did you understand? Sure. Let me write this down. I believe that then you will be able to understand. Standard enthalpy change for the formation of 1 mole of a compound, 1 mole of a compound from where? From its elements. From its elements in their reference state. In their reference state. Okay. So what am I saying? I'm saying that the constituent elements in their most stable state and 1 mole of compound should form. What am I saying? I have said that the constituent elements, those which form the compound, they should be in their stable state, and 1 mole of compound you must get. If you get 1 mole of compound, then only you are going to call it standard enthalpy of formation. Are you getting it? Only then you are going to call it as standard enthalpy of formation. What is written? Please read it, everybody. Standard enthalpy change for the formation of 1 mole of compound. Suppose NaCl is forming. Now for NaCl formation, you have to have 1 mole of NaCl compound that has formed. From where? From Na, which is in solid state, and Cl, chlorine, stays in gaseous state, and sodium is in solid state. So from that solid state and from the gaseous state, you must get NaCl 1 mole which is in solid state. Do you get it? Do you get it? Do you get it, everybody? Go Green India. I think I've just repeated. Now did you understand? Now did you understand? Yes or no? Acha. After all of this is done, okay, now all of this is done. Now we will come to something called as Hess law of constant summation. Shall we? Yes. Now this is very important, everybody. Although the name is very weird, it is just Hess law of constant heat summation. Constant heat summation. But are we going to say this again and again? Every time I will say Hess law of constant heat summation, Hess law of constant heat summation. No, I will say Hess law. Okay. What is Hess law? Hess law suggests that if the reaction is taking place, acha, I'll give you an example. Everybody, do you remember inorganic chemistry? In inorganic chemistry, what happened? If you want to form 1 mole of NaCl, yes. If you want to form NaCl, 1 mole of NaCl, let's say, okay, chemistry. So we talk a little bit in chemistry language. We have 1 mole of NaCl forming. Now for NaCl to form, from sodium, first I have to take away 1 electron to make it Na plus. I have to take one electron away from it. So I will be using some amount of ionization energy. After this ionization energy, now what will happen is this chlorine, it will have electron gain enthalpy. It will take in the electron and release some energy. So electron gain enthalpy, right? After that, there will be a bond formation energy, right? Bond formation energy, these two will come together. After they come together, then they will go into the solid state. So all of these processes are happening. All of these processes are happening. So Hess law says that when there is a reaction, when it is forming in 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, let's say that 10 steps it is taking. So if the reaction takes place in several steps, or let's say that the reaction takes place in 10 steps, then the standard reaction enthalpy is the sum of standard enthalpies of the intermediate reaction. Do you understand? Do you understand? Yes, do you understand, everybody? Did we get it, guys? What is Hess law? So what am I saying is, I'm saying that if a reaction takes place, I don't feel like writing, guys. I don't feel like writing. Can you guys write it down? If a reaction, chalo, let me write it down only. If a reaction takes place in several steps, or 10 steps, or 100 steps, or whatever steps, yes, in several steps, then what will happen? Then it's standard reaction enthalpy, then its standard reaction enthalpy is sum of standard enthalpies of the intermediate steps of the intermediate reaction. Now whatever reactions are happening, right, wherever you are requiring the energy, you have to understand that you will add all of them, and then you are going to get your standard reaction enthalpy. Get it, everybody? Great. Yes. Now you remember there is standard enthalpy of atomization. What is, I know JEE does not require, but I still want to, but I still want you to, I want to give you the notes, so that is why I'm writing it. Anyway, now you must know that there is something called a standard enthalpy of atomization. What is standard enthalpy of atomization? Basically what you're doing is you break a bond and make an atom. Usually what happens, you do not have atoms. Usually in chemistry you get molecules, because the atoms, they do not retain their chemical properties and they don't want to stay like this. The molecules, they are the smallest units which can retain the properties of a compound. So you usually have a molecule, but what do? You want to break it down, because let's say that chlorine in its reference states like to stay as Cl2. Now Cl2 is what? It's a molecule. I don't want Cl2. Why would I need a Cl2? I don't want a Cl2. I want only one Cl. I want Cl, because that can only take that one electron, right? So what will I do? Break the bond. I'll break the bond. Once I break the bond, what will I get? I will be getting a one single atom, and that is called a standard enthalpy of atomization. So what is standard enthalpy of atomization? If somebody asks you a definition, you will say enthalpy change or breaking one mole of bonds completely to obtain atoms in the gas phase. That is just standard enthalpy of atomization. Now if you have, so right now everybody, I just told you that Cl2, what is Cl2? Cl2 is diatomic molecule, right? There are two atoms here. Now for a diatomic molecule, your enthalpy of atomization is equal to enthalpy of bond dissociation. But suppose you have a polyatomic molecule like NH3, like H2O, like methane, CH4. At this point of time, everybody, at this point of time, if you have NH3, so now N, let's say that this is N, okay, let's say that NH3, right? Let's say that this is your NH3, yes, this is NH3. Now if you want to break this bond, let's say that I require only I require more force, right? I require more energy. To break this was easy, and this even more easy. So now do you understand what I tried to do? I tried to tell you that here breaking each and every bond was not equal. Yes, we did not require equal energy to break these bonds. We did not require equal energies to break these bonds in case of a polyatomic molecule. And at that point of time, we will be using mean bond enthalpy. What will we be using? We will be using mean bond enthalpy. Yes, that means that you will be adding all of them and then take the mean. You all know mean, right? What is mean? That's it. You just take the mean. After you take the mean, average, yeah, mean, you know, in statistics you have mean. I think today only Namrata ma'am has taught you statistics, isn't it? Yeah, so you all know what is mean. I don't have to tell you. So you take the mean bond enthalpy. Now what is lattice enthalpy, everyone? What is lattice enthalpy? Lattice enthalpy, I just told you now. The enthalpy change which occurs when 1 mole of an ionic compound dissociates. For example, if I have NaCl, now this NaCl, what am I going to do? This NaCl, when I break it down, NaCl is a lattice. NaCl is a lattice. So when I break it down and I break them down into their gaseous state, the atoms are in their gaseous state. That is called as your lattice enthalpy. All right. And one more standard enthalpy is combustion. Standard enthalpy of combustion. अरे जला दो किसी चीज को, like burn it down. That will be standard enthalpy of combustion, right? No, just kidding. Acha, listen to me. Standard enthalpy of combustion is, everybody, I don't have to join them. It gets joined. It has holes and stuffs like this, right? Anyway, so as I was telling, enthalpy change per mole of a substance when it undergoes combustion. See, that is what, you take 1 mole of a substance, burn it up. When you burn it up, whatever enthalpy change that occurs and all the reactants or products are being in the standard states, and then you get your standard enthalpy of combustion. All right, done, everybody. Lattice enthalpy is done. Now, let us understand Born-Haber cycle. This is very important, bachos. Born-Haber cycle. Now, Born-Haber cycle is actually slightly related to Hess's law, related to Hess law and whatever I have just explained to you. So, Born-Haber cycle, everybody, please pay attention. We are going to understand this. Yes, this is your Born-Haber cycle, and we are going to simply use the example of NaCl, right? Because I've just told you. So, let's say that we have here NaCl, right? This NaCl is in solid state. Now, how can I form NaCl? There are two ways I can form NaCl, right? I have, let's say that I can take Na plus in gaseous state, and I take Cl minus in gaseous state, right? Either by this formation I can do, yes, either by this process I can do this, or there is a possibility, everybody, have a look, guys. Or what I can do is I can take Na in solid state, all right, and what I can do is I can take Cl2. I will not write here Cl2, I will write here half Cl2 in gaseous state, and then I can form this NaCl, right? I can do this also. Now what will happen is this Na which is in solid state, I cannot directly use it. Can I? Can I directly use this? I cannot directly use it, right? I cannot directly use it, everybody. So right here, you will see that what will I have to do? I will have to convert this into Na gaseous state. And for this, what will I require? I will require sublimation enthalpy, right? I will require standard enthalpy of sublimation here, all right? Yes. Now from this Na gaseous state to I have to convert this into Na plus gaseous state. Now what do I have to do? I will need some ionization energy. Yes, I will require a little bit of ionization enthalpy to convert it into Na plus, right? Very good. Now here what do I have? Check it out, guys. Here I have Cl2. This is a molecule. I cannot use a molecule. I cannot use a molecule, but choose. What do I need? I need an atom. So what do I have to do? I have to use delta dissociation enthalpy, right? I will use delta. So I will use standard enthalpy of dissociation divided by 2 because what? Cl2, right? After doing this, now I will be getting chlorine in gaseous state. After I have got chlorine in gaseous state, do you remember, bachus? I've just told you, now you will have to give delta electron gain enthalpy. You will need standard enthalpy of electron gain. You will need electron gain enthalpy. Am I right? Yes, you will need electron gain enthalpy to convert it into Cl minus. And then there will be delta lattice. Yes, there will be lattice enthalpy in picture, and then you will get the process. So either this can be this one step process, or it can be this multi-step process, Right, everybody? Right? So what did Hess law said? Hess law suggested that what you're going to do is, for either, he said that the first step process will be equal to, the enthalpy will be equal to the multi-step, or the multi-step, whatever is happening. So here, let's say that this is enthalpy of formation. What is this? This is your enthalpy of formation right here. Okay, this is your enthalpy of formation right here. So what I can do is, I can write it as delta, delta F H naught is equal to, what are the things that I use? I have standard enthalpy of sublimation, right? I have standard enthalpy of sublimation, then I have the then I have ionization enthalpy, right? Then what do I have? Then I have delta dissociation enthalpy, right? I have dissociation enthalpy divided by 2. Then I have electron gain enthalpy, right? And I have finally lattice enthalpy. So together this will be equal. And this, my dear students, is your Hess law. Do we agree on this, everybody? Yes. Do we understand this, guys? Do we understand this, everybody? Yes, 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 yes. Great. Now we have seen that there is something that is called as spontaneity, right? Have we noticed? Spontaneity. What is spontaneity? You must have seen that there are some reactions, or there are certain reactions which are spontaneous in nature. That means they occur on their own. Some processes, they occur on their own, right? So a spontaneous process is usually an irreversible process, and they may not be reversed by some external agency, right? So whatever you do, you might not be able to reverse it, okay? Now the question is that who decides this spontaneity? Who decides that, acha, so global warming is happening and there will be, forest fire just like that? Who will tell us this? Who is going to tell us that yes, forest fire is spontaneous? Yes, sodium will burn on its own. Who is going to tell this? This, my dear students, we have noticed, most of the time we have noticed that when there is a decrease in enthalpy, that means again bond formation. When there is a bond formation, everybody, what happens? Energy gets reduced. Energy gets reduced, that means stability comes into picture, right? Remember, we have studied this. Yes. So we have normally seen that when there is a decrease in enthalpy, that means that whenever somebody wants to release its energy and say that no, 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 I want to get stable, I want to get stable, that time this will be a spontaneous reaction. Are you getting my point? Are you getting my point? But that's not the case. Because there are also certain other examples where we see that energy is not released. It is an endothermic process, but it is spontaneous. We have noticed that there are certain endothermic process which are spontaneous. So now we understand that acha. So only energy reducing and becoming stable, that's not the only factor for spontaneity. Yes. So the question is still existing, everybody. What decides spontaneity? You know who? You know who, everybody? It is entropy that decides spontaneity. And what is entropy? Entropy is the degree of randomness. What is it? Entropy is degree of randomness. Okay? Again, so now let's understand. What is entropy? For examples, everybody. For example, everyone. If there is no class teacher in your class, what will you do? In your school, it's completely a fish market, isn't it? Everybody, you will all start shouting and blah 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 and all of these is right? Now let's say your principal ma'am comes. The moment principal ma'am comes, what is your principal ma'am going to ask? Your principal ma'am is not going to ask you that bell rang, it has been 5 minutes, why is the teacher not here? The teacher went to hospital, the teacher went to washroom, the teacher went to meet a parent, the teacher went to the gate. What happened to the teacher? No one is asking. Nobody is going to ask you this. Principal ma'am will only ask you one single question, that is, why is teacher not there? But he or she is not going to listen to the explanation that you give. So do you understand that entropy is a state function? Entropy is a state function. It is not a path function. Nobody cares where the teacher has gone. The teacher is near the gate. The teacher is in the washroom. The teacher has fallen down and broken his leg. Doesn't matter. Why is the teacher not there? The bell rang, the teacher is supposed to be there. Why did you guys make noise? That's it. And then when the teacher was not there, what was it? Randomness. When you were doing this masti, when you're making this as a fish market, that was randomness. Because there is a possibility that one of you will throw the book like this and somebody will get hit like this. One of you will be eating your tiffin like this. One of you will throw some water on somebody else, right? Degree of randomness. Nobody can predict. Now, in a school, what are you trying to do? What are you trying to do? Your principal ma'am's aim is to bring this randomness to a very low energy. And that is why what happens? And that is why when the teacher comes, the moment you see principal ma'am, you are all like, good morning, miss. We didn't do anything, ma'am. You will do this. You will do this. So here what are we trying to do? We are trying to bring the disorder less. And whenever a system will try to bring its disorder less, spontaneity will occur. Now do you understand? Now do you understand, everybody? Yes? Great. Quickly, do we understand? Can I have some EPBT, guys? Can I have some EPBT? Yes? Everybody, do we understand? Great. So how to quantify entropy? How do we quantify this? We all know that delta S is directly proportional to Q, right? Yes? Now, chalo. Now I think it is time to, it is time to talk about it. Yes? Yeah, you're trying to prove yourselves that you are all innocent and everything, right? You do that, exactly. Now, let us understand that how do we represent this entropy mathematically, okay? So, mathematically, we all know that, okay, one second. Delta S is, yes, delta S is directly proportional to Q, which is heat, all right, which is added to the system. And delta S is inversely proportional to temperature of the system. Now you will be like, how is that possible? How is that possible? Ma'am, how is it? We all know that if temperature increases, degree of randomness is supposed to increase, but no. Think about it this way. Think about it this way, okay? Now, let's say that in a class, there is already no class teacher. Okay, there is already no class teacher. Now, if there is no class teacher, suddenly your friend comes in and they say that, guys, games period. What will you do? Nothing. Some of you might not even hear it because you are all throwing stuff and eating tiffin and dancing and everything you are doing. You are not able to listen to it because your randomness is already much. You are already random. So you are not able to hear the fact that now it is your games period. But imagine now a class is absolutely sitting quiet and suddenly somebody comes and says that, guys, games period. Where will the randomness be more? In one case, it is already random. In one case, it is already random. So now if you introduce a little bit of more factor for randomness, it's not going to affect so much. But in one case where randomness is not there, you increase temperature, this is going to go shoot up with the randomness. Do you get my point? Why did I say that the delta S is inversely proportional to the temperature of the system? Do you get it? Do you get it, everybody? Yes. So that means that together now we can say that delta S is equal to Q by T. Delta S is equal to Q by T. Alright. Now entropy, me running to the playground, only if you have heard it. If you haven't, then it's not going to affect you. Chalo. Now entropy for reversible and irreversible processes, everybody. Okay. So for reversible process, everyone. For reversible process, guys, it is, yes, delta S universe is equal to 0. And for irreversible process, everybody, for irreversible process, yes, delta S of universe is greater than 0. Okay, it is greater than 0. All right. And under isothermal conditions, delta U is equal to 0 for both reversible and irreversible processes. Okay. Now we finally come to the last bit of it, everybody. Solid liquid. Bacha, solid liquid mein to anyway it does not happen so much, no? In solid and liquid, we already know that the degree of randomness is very less, isn't it? The degree of randomness is very, very, very less. Mohi, do you understand? Great. Now we finally come across the Gibbs energy and spontaneity. Everybody quickly pay some attention, everybody. We come to Gibbs energy. Gives energy and spontaneity. Now we have understood that this spontaneity, it depends on delta H and delta S, right? So this Gibbs function is given by G, and we say that G is equal to H minus T delta S. This is called as Gibbs Helmholtz equation only if you introduce, actually it's not T delta S here, let's write here TS. Let's write here TS, but we can also write it as delta G is equal to delta H minus T delta S. Am I right? And this becomes your Gibbs-Helmholtz equation. Now, if delta G is negative, the process is going to be spontaneous. Yes, that means that, okay, now write this down. These two factors are very important, everybody. That delta G negative when the process is spontaneous. That means delta H minus T delta S is lesser than 0. Alright. When is delta G positive? Delta G is positive when you have what? When the process is non-spontaneous. When the process is non-spontaneous, at that time you have this. Now, my dear students, we finally come across the second law of thermodynamics, and your second law of thermodynamics dynamics is in exothermic reactions, the heat released by the reaction increases the disorder of the surroundings and overall entropy changes positive, which makes the reaction spontaneous. Can somebody please look up the syllabus once and tell me that is third law of thermodynamics present or not? Is third law of thermodynamics present in your JEE syllabus or not? Okay. Here guys, here is your second law of thermodynamics, that no cyclic engine is possible which takes heat from one single source and in a cycle completely convert it into work without producing any change in surrounding. That means in an irreversible process, entropy of universe increases but it remains constant in a reversible process. This is what is bringing us to your second law of thermodynamics. All right. Yes. So we are done with everything, guys. We are done with entropy. We are done with second law of thermodynamics. We are basically done. Carnot engine is deleted. Yes, but Carnot engine is in physics, bacha. Carnot engine is in physics. I don't think it's there in your this exam. It's not here. Can somebody tell me that in thermodynamics, third law of thermodynamics is deleted or is it there? Can somebody? Third law is reduced, right? It's not there. Thank you so much. So there is no point in reading third law then, okay? So we're done till second law of thermodynamics. We're done with it, everybody. Now let us solve one or two questions and then I will let you all go, okay? And then I will let you all go. I think we are almost done, everybody. Let's quickly solve one or two questions. Sure. This question, if X mole of ideal gas at 27 degrees Celsius expands isothermally and reversibly from a volume of Y to 10Y, then the work done is. Can we answer? Can we answer? The answer is W is equal to minus 2.303 nRT log V2 by V1. Yes? And what is this equal to? That means I can also write this as nRT minus nRT ln V2 by V1. Can I not write this? I can write this. Now, what is given to you? See, you are given X mole, you are given 27 degrees Celsius. So 27 degrees Celsius plus, if I do 273, I will be getting 300 Kelvin, isn't it? So minus 300 Kelvin multiplied with X mole, and I know that R and T, R let's keep it as it is. Okay, let's keep R as it is. Now with R, you have ln, and then you are given V2 is a 10Y and V1 is Y. So Y and Y cancel. So this is your answer. This is your answer, minus 300 XR x r ln 10, isn't it? This is your answer, everybody. Yes, guys, this is your answer. Chalo, next question. What is the difference between heats of reaction at constant pressure and constant volume for our reaction? Guys, I believe that we have done this very recently. Yes, we have just studied this concept, isn't it? Now, we all know that delta H is equal to delta U plus delta NGRT. Do we know this? Yes? Do we know this, everybody? We do know this, isn't it? We do know this. Now, what is given to us is C6H12 liquid, 9O2 gas. Yes, 9O2 gas, 6CO2 gaseous plus 6H2. Now, we know that we only require the gaseous part, isn't it? We only require the gaseous part. So, we have 6 CO2 and we have 9O2. These are the gaseous part. So, that means that my delta Ng is equal to 6 minus 9, which is equal to minus 3, right? So now delta H minus delta U is equal to minus 3 multiplied with what is R value is 8.314 or 8.134 multiplied with, I can do 300 here, yes. If I calculate this, how much do you get, guys? If you calculate this, how much do you get? I believe that it should be it will be minus minus this, yes, in kilojoule, right? I believe that it should be option C. Not very sure. Yes, it is option C. I believe it is option C. Okay, next question. In which of the following cases the reaction is spontaneous at all temperatures? Now we know that when delta G is lesser than 0, that is when it is negative, that is when it is spontaneous. That is when it is spontaneous. So that means that we all know that delta G is equal to delta H minus T delta S. Now when is delta G going to be negative? Delta G has to be negative. For delta G to be negative, delta S has to be negative, because negative and this negative will become positive. And then if this is also negative, only then I will get delta G as negative. Am I right? Very good. So wherever you see that delta H is positive, don't even consider it. This is wrong. No. This is possible. This is possible. And I can also have my delta S also has to be negative, isn't it? So I believe that it is option C once again, or is it option B? Option B. It can be option B, yes. It has to be option B. Yes, because this can be positive. Delta S can be positive and then this can be negative. But if this is also less, then I will get a negative, isn't it? Then I will get a negative, yes. So yes. Option B. Option B is the correct answer, guys. Option B is the correct answer. Acha, so I believe that we are done with everything. Factors, enthalpy, I have almost completed everything, bacha. Almost completed everything. Hess law is done. Yes, Hess law is done. I've completed all of these. Acha, here is a question. Do you think that you will be able to take 2 questions as homework and you will be able to do it? Do you think that you will be able to take 2 questions as homework and you will be able to solve it on your own? Because I can give you this question as homework and I will give you these 2 questions as homework. Both of them are PYQ. Both of them are PYQ, everybody. Try and solve it. If you are not able to solve it, by tomorrow, I will solve the question, handwritten, and then I will give it to you, okay? And then I will send it to you in the Telegram channel. Now, my dear students, last but not the least, everybody, do not forget that in Vedantu, we have launched JEE test series, which is absolutely free of cost. Here is your CBT mode. This is a computer-based mode. It will be completely in simulation with your JEE exam pattern, and it will also follow JEE new syllabus. So please go ahead. All you have to do is, link is in the description box. Just go and start appearing for the test, everybody. Okay? And apart from that, every single day you get Vedantu daily practice problems, and please join the Telegram channel, because in the Telegram channel you will be getting the notes. In the Telegram channel you will be able to get the questions and everything. So I think it is going to be best of both the worlds. So just go and join and appear for the test, because it will be great for you. And finally, with this note, everybody, thank you so much. But do not go anywhere because Shreya sir is going to come up now and he is going to take you through ray optics, everybody. So, chalo guys, tata, bye-bye. Have a nice night. Good night, everybody. Have your dinner and stay up